millions of years ago, Earth had a very different arrangement of oceans and continents. Instead of familiar coastlines, broad inland seas spread across the interiors of landmasses, and warm, high sea levels flooded low-lying regions. When the surface of this planet is imagined from above during the late Cretaceous, much of it is covered by shallow, sunlit water that formed ideal habitats for marine reptiles. Now the view shifts beneath those waves. Light filters down through green water, plankton drifting like dust in a submerged sky. A shadow appears overhead, long and narrow, moving with steady confidence. At first, it resembles the outline of a large shark, but as it passes closer, the true shape emerges. A 15-meter mosasaur, a giant sea lizard with a deep, muscular tail, paddle-like limbs, and a skull lined with conical, recurved teeth. In this environment, it is the dominant hunter. These animals were not dinosaurs. They belonged to a separate branch of reptile evolution, marine reptiles that had returned to the sea. Mosasaurs descended from land-dwelling lizards that once walked on coastal plains and river deltas. Over time, those early forms adapted to swimming, their limbs flattening into flippers and their tails becoming powerful propellers. Because of this transition, mosasaurs share ancestry with modern monitor lizards and snakes, and their flexible skulls and double-hinged jaws reveal this connection. They did not swim alone. During this time, Cretaceous seas supported a diverse cast of marine reptiles. Long-necked plesiosaurs cruised slowly with 4 beating flippers, their small heads searching for shoals of fish. Short-necked pliosaurs, though less common by the late Cretaceous, represented older lineages of large-jawed predators. Broad-shelled sea turtles glided between surface and seafloor, while the last ichthyosaurs, shaped like streamlined dolphins, were fading from the record. Together, these groups built complex ecosystems, yet mosasaurs rose to the apex role in many regions. This dominance unfolded long before whales and giant sharks appeared. The time frame lies in the final chapters of the Mesozoic era, tens of millions of years before marine mammals evolved from land mammals. The breakup of the earlier supercontinent Pangaea had already reshaped the planet. As the crust fractured and plates drifted, new ocean basins opened and long seaways flooded continental interiors. This process created broad, warm, nutrient-rich corridors, such as the western interior seaway of North America, where mosasaurs and other marine reptiles flourished. What forces within Earth's mantle drove these changes, and how did shifting plates guide the rise of giant sea lizards? To understand that story, it is necessary to trace the deep history of oceans and continents, from their early formation to the Cretaceous world. This journey will move through the tectonic events that built seaways, follow the evolution of marine reptiles from small shoreline hunters to enormous predators, and end with their sudden extinction. As a result, an ordinary lineage of lizards will be seen transforming into rulers of the ancient seas. To understand how ordinary lizards could one day dominate the seas, the story must pass through a very unusual chapter in Earth's history, the age of Pangaea. Hundreds of millions of years before the Cretaceous, the planet's land was drawn together into one vast supercontinent, and this arrangement quietly prepared the stage on which later marine reptiles would rise. Pangaea formed during the late Paleozoic era, roughly 335 million years ago, as earlier continents collided along immense mountain belts. During this time, plate motions slowly pushed scattered landmasses together, welding them into a single giant block that stretched almost from pole to pole. This process did not happen quickly. Over time, subduction zones consumed older ocean crust, volcanic arcs grew, and the remaining oceans narrowed until only one global superocean surrounded Pangaea. A single landmass of this size had powerful effects on climate and oceans. Deep inside Pangaea, far from any coast, the interior regions experienced strong seasonal extremes, with very hot summers and cold winters. Along the margins, however, the supercontinent possessed an enormous length of coastline. Long, narrow shelves formed where land met sea, creating broad, shallow waters. At the same time, the superocean's circulation differed from modern patterns because of this unusual geometry of continents and basins. These conditions mattered for marine life. Shallow continental shelves tend to support rich ecosystems because sunlight can reach the seafloor and nutrients are often concentrated there. During the early Mesozoic, after the end Permian extinction, new groups of marine reptiles, such as early ichthyosaurs and plesiosaurs, began to exploit these habitats. Their success showed how tectonic arrangements of continents could influence which organisms flourished along the edges of the supercontinent. Pangaea did not remain stable forever. Around 200 million years ago, rifts opened as mantle heat thinned and stretched the crust. These rifts deepened into new ocean basins, and lava poured out along long fissures. As the supercontinent fragmented, separate landmasses drifted apart, and the single superocean was replaced by multiple interconnected oceans. What did this mean for future sea lizards? The breakup of Pangaea created wide, shallow epicontinental seas that flooded low-lying regions of the continents. During the Jurassic and especially the Cretaceous, rising sea levels and continued rifting allowed water to invade the interiors of landmasses, forming features such as the Western Interior Seaway of North America. These warm, relatively enclosed seas were ideal environments for marine reptiles to diversify, hunt, and grow to large sizes. Earth's history can therefore be viewed as a linked sequence of stages: late Paleozoic assembly of Pangaea, early Mesozoic stability of the supercontinent, and later fragmentation that led into the Cretaceous greenhouse world. As a result, the oceans in which mosasaurs evolved were direct products of decisions made deep in the planet's mantle, expressed through slow plate motions at the surface. To understand why giant sea lizards could evolve and dominate these Cretaceous seas, the narrative must now move even further back, to the origins of continents, oceans, and the plate tectonic engine that drives them. How did the planet first develop moving plates, floating continents, and long-lived oceans that could host such predators? To reach the age of giant sea lizards gliding through warm Cretaceous seas, the story must first pass through a far harsher chapter in Earth's history. Long before any supercontinent assembled, the planet itself was still learning how to have a stable surface, lasting oceans, and an atmosphere that did more than choke and burn. More than 4.5 billion years ago, shortly after it formed, Earth was a violent, molten world. The young planet was still growing as large bodies crashed into it, releasing enormous amounts of heat. Because of this intense bombardment and the decay of radioactive elements, much of the outer layer melted. Instead of blue oceans and solid continents, the surface consisted of vast magma fields, impact basins, and temporary crust that fractured and sank back into the mantle again and again. During this time, the atmosphere was nothing like the breathable air of the later Cretaceous. Volcanic eruptions released carbon dioxide, water vapor, sulfur gases, and other compounds, creating a dense, toxic envelope around the planet. There was no oxygen to support animals, no protective ozone layer, and no stable climate. Yet this hostile mixture held the seeds of change, because as the surface slowly cooled, water vapor began to condense. Over time, that condensation turned into relentless rain. Thick clouds surrounded the planet as water fell for immense spans of time. Some of this water came from the interior through volcanic outgassing, and some arrived on impact, carried by icy comets and water-rich asteroids. As a result, liquid water began to collect in low areas of the crust. These growing basins merged and deepened until Earth finally possessed continuous global oceans, dark and mineral-rich, spreading over most of the surface. As the outer shell cooled further, early crust began to stabilize. The first solid rocks formed a thin, fragile skin above the hotter mantle. This process produced two main types of crust. Dense oceanic crust, made mostly of basalt, formed the floors of the young oceans. Lighter, more buoyant continental crust, enriched in silica and other elements, began as small scattered fragments. These early continental seeds were nothing like the broad continents familiar today. They were isolated blocks that survived repeated cycles of heating, breaking, and partial destruction. Because of this continuous recycling, no Pangea-like supercontinent yet existed. Instead, the planet's surface hosted protocontinents and volcanic island arcs drifting on a mantle that was hotter and more active than it is now. Plates moved faster, subduction zones consumed crust rapidly, and mountain belts rose and eroded on shorter timescales. The arrangement of land and sea changed often, leaving no long-lived configuration to resemble later supercontinents. If an observer could hover above this early Earth, would the planet even be recognizable? There would be no familiar outlines of Africa or North America, no chalky seafloors, no shallow continental shelves ready to host coral reefs and marine reptiles. Instead, there would be a dark global ocean, shrouded in thick clouds and steam, dotted with glowing volcanic chains and small, unstable landmasses. Yet hidden within this restless scene were the essential conditions for everything that followed. Long-lived oceans, surviving continental fragments, and an atmosphere slowly adjusting to new chemical reactions set the stage for the first life, the rise of oxygen, and later, the assembly of true supercontinents. How did this shifting, ocean-dominated planet progress from scattered protocontinents to the giant landmasses that would one day frame the hunting grounds of the sea lizards? To understand how scattered protocontinents could ever gather into a single giant landmass, it is necessary to look beneath Earth's surface. The planet's rigid outer shell is not one unbroken layer. Instead, the crust and the very top of the mantle form a mosaic of tectonic plates that slowly shift, collide, and separate. Over time, this restless shell has reorganized the positions of oceans and continents again and again. These plates move because the interior of the planet is still hot. Heat rising from the deep mantle creates slow convection currents, which drag plates along. At the same time, gravity helps older, colder plates sink where they bend downward, and newly formed crust near ridges slides away as it thickens. This process may seem gentle on human timescales, but over tens of millions of years, it can close entire oceans and weld distant lands together. The main engines of this motion lie along plate boundaries. At mid-ocean ridges, hot mantle material rises, partially melts, and creates new oceanic crust. As this new crust spreads away from the ridge, it carries attached continents with it. Farther along, at subduction zones, aging sea floor becomes dense enough to plunge back into the mantle. There it sinks, drags the rest of the plate, and helps recycle the crust into deeper layers of the planet. This continuous creation and destruction of seafloor slowly redraws the map of Earth. Oceans open when plates pull apart, and they close when subduction zones consume the intervening crust. Because of this, continents that were once separated by wide basins can be driven back together. Mountain belts rise where they collide, while other margins stretch and thin, preparing for future rifting and new oceans. Over long spans of Earth's history, these interactions have produced a repeating pattern known as the supercontinent cycle. During this time, scattered continents drift toward one another, assemble into a single vast landmass, and then eventually break apart again. Earlier supercontinents, such as Columbia and Rodinia, formed through this same sequence of collision, thickening, and later rifting. Each full cycle may take hundreds of millions of years to unfold. The assembly and breakup of supercontinents have deep environmental consequences. When continents cluster together, coastlines shorten, interior regions become more extreme in climate, and ocean circulation patterns shift. When they rift apart, long, shallow continental seas can flood over low-lying crust, raising global sea levels and creating broad, sunlit habitats for marine life. As a result, entire ecosystems can appear, spread, and vanish as the geometry of land and ocean changes. Here, a pattern interrupt in Earth's story appears. The solid ground underfoot is part of a very slow, global conveyor. What seems fixed is actually migrating. This slow motion set the stage for Pangaea, which was only one chapter in a much older cycle. Its later breakup would carve new ocean basins and broad inland seaways, including the Cretaceous waterways that became prime hunting grounds for the giant sea lizards of the age to come. That slow, hidden conveyor of plates did more than assemble and break apart a single supercontinent. It repeatedly rebuilt the very stage on which life experimented. Long before Pangaea dominated the map, earlier cycles of drifting and collision had already created scattered continents, broad continental shelves, and intricate shorelines where land and sea met in shifting patterns. During this time in the late Paleozoic, Earth's oceans were arranged very differently from the Cretaceous seaways that would later host giant sea lizards. Continents were still in the process of converging, and many sat in tropical or subtropical zones. Shallow seas flooded low-lying regions of the crust. Sunlight penetrated these waters, fueling dense communities of algae, invertebrates, and early fishes. This process built complex food webs along the edges of the continents, turning continental shelves into laboratories for evolutionary change. Yet the story of marine reptiles begins even earlier, with the first vertebrates that crawled onto land. In the Devonian and Carboniferous periods, lobe-finned fishes gave rise to early tetrapods that developed limbs, lungs, and stronger skeletons. They left the water to exploit new habitats among riverside plants and swamp forests. Over time, some of their descendants reversed course. Limbs widened into paddles, tails flattened, and bodies became more streamlined as certain lineages moved back toward aquatic life. Why did this happen again and again? Because of this back and forth, a pattern emerged in Earth's history. Whenever rich coastal ecosystems and shallow seas surrounded the continents, land vertebrates repeatedly invaded the water. Amphibian-like forms hunted in lagoons, early reptiles patrolled tidal flats, and some began spending most of their lives offshore. As a result, the idea of vertebrates returning to the sea was well established long before the dramatic reptiles of the Mesozoic. The ocean was not a blank canvas. It was a familiar arena that life had entered and left many times. After the catastrophic end Permian extinction, this pattern took on a new intensity. In the Triassic, as early Pangaea stretched across much of the planet, vast coastal margins bordered a single great ocean, the Panthalassa, and smaller inland seas such as the Tethys. In these recovering waters, the first true marine reptiles appeared, streamlined ichthyosaurs, with bodies that converged on the shape of modern dolphins, evolved powerful tails for propulsion and large eyes for hunting in dim light. Alongside them, early sauropterygians, including the ancestors of later plesiosaurs, developed strong limb girdles and broad paddles for underwater flight. These Triassic pioneers evolved in oceans governed by different wind patterns, currents, and climates than the later Cretaceous seas. Deep circulation was influenced by the arrangement of a nearly global supercontinent rather than widely separated landmasses. This meant that the pathways for migration, the distribution of nutrients, and the locations of productive coastal zones did not match the future world of mosasaurs. Yet the basic solutions to living in the open ocean, streamlining, efficient swimming, air-breathing lungs, and live birth in some groups, were already in place. By the time Pangaea began to rift apart and new ocean basins opened, marine reptiles had a long evolutionary history behind them. When mosasaurs finally emerged in the late Cretaceous, they entered seas already shaped by millions of years of reptilian innovation. The map, however, had changed. Instead of one great ocean, there were broad interior seaways and young Atlantic basins. In the next part of the story, These new waterways would become the hunting grounds for the largest lizards the planet has ever known. To understand how those Cretaceous seaways appeared, the story must step back to a time when almost all land was fused together. Hundreds of millions of years before mosasaurs hunted in young Atlantic basins, the continents themselves were converging to form a single giant landmass, Pangaea. During this time, the arrangement of oceans and continents on Earth was moving toward one of the most extreme states in the planet's history. In the late Paleozoic, several large continental blocks drifted across the surface, driven by slow motion in the mantle below. Laurasia occupied the northern hemisphere, Gondwana lay to the south, and smaller terrains and island arcs approached along subduction zones. Over time, these fragments collided, crumpled, and welded together. This process raised mountain chains such as the ancestral Appalachians and Urals as the last gaps between the continents closed. When the collisions ended, nearly all major continents had locked into a single supercontinent. Pangaea stretched almost from pole to pole. Around it, like a vast ring, lay a single global ocean known as Panthalassa. This ocean covered most of the planet's surface and, in many regions, lacked the complex chains of continents and island arcs that break up modern oceans. As a result, huge areas of Panthalassa were deep, open, and relatively featureless. Along one side of Pangaea, however, the situation was more intricate. There, between projecting continental margins and smaller microcontinents, a narrower, more complex seaway developed, the Tethys Ocean. This body of water wound along the equatorial belt of Pangaea. It contained island chains, submerged ridges, and broad continental shelves that created a varied set of marine environments, very different from the empty central Panthalassa. Because of this arrangement, Earth's coastlines became both long and highly irregular. The interior of Panthalassa was dominated by deep water, but around Pangaea's edges, broad shallow shelf seas formed where the crust of the continents dipped gently beneath the ocean. These shelves were flooded by warm, sunlit water and supplied with sediments and nutrients from nearby land. Over time, such coastal and shelf regions would become prime habitats for diverse marine life, including the distant ancestors of later marine reptiles. The climate of this supercontinent world was also distinctive. Far from the coasts, the interior of Pangaea lay far from moist ocean air and tended to be dry, with large deserts and extreme seasonal temperature swings. Near the margins, strong monsoonal wind patterns developed as land and ocean heated and cooled at different rates. This process drove intense seasonal rains along some coasts and influenced ocean circulation in both Panthalassa and the Tethys. Temperature gradients between equatorial Tethys waters and cooler Panthalassa regions helped control currents, upwelling, and nutrient distribution. These patterns shaped where plankton bloomed, where reefs grew, and where early marine ecosystems flourished. Yet the world of Pangaea was only a starting point. When this giant landmass finally began to tear apart, the same forces that had assembled one world ocean would carve out the fragmented Cretaceous seas, where giant lizards would one day rule. How did that breakup unfold, and how did it turn scattered coastlines into vast interior seaways? When Pangaea finally began to fail, the change did not happen in a single violent moment. It unfolded as a long sequence of cracks, uplifts, and foundering blocks of crust, turning one supercontinent into a patchwork of drifting plates. During this time, the solid outline of Pangaea gave way to widening rift valleys and narrow seaways that would eventually reshape the entire ocean system. The first major tiers opened in the early Mesozoic, as deep mantle heat rose beneath the thick continental interior. This process stretched the crust between what would become North America and northwestern Africa, and between North America and Eurasia. Long rift zones formed, filled with volcanic rocks and sediments, and then sank below sea level. Over time, these flooded rifts expanded into the early Atlantic and related basins, transforming former inland regions of Pangaea into young ocean floors fringed by fresh continental margins. As the continents pulled apart, something subtle but powerful happened along their edges. The single smooth shoreline of Pangaea broke into many smaller coasts, bays, and embayments. New continental shelves formed as the stretched crust thinned and gently subsided beneath shallow water. Because of this, the total length of coastline increased dramatically, and the area of sunlit, shallow seas expanded. These shelves became ideal zones for reefs, plankton blooms, and complex food webs that could support large marine animals. To the south and east, the Tethys region changed from a broad equatorial gulf into a complex network of seaways. As fragments of Gondwana and pieces of Eurasia shifted, narrow ocean arms opened, widened, and sometimes closed again. This evolving Tethys Ocean contained island chains, enclosed basins, and broad platforms that acted as stepping stones for marine organisms. Over time, it became a major corridor for dispersal, allowing lineages that evolved in one region to spread into distant basins, and, later, providing routes for the radiation of advanced marine reptiles such as mosasaurs. The breakup of Pangaea also altered the invisible architecture of the oceans, their currents and temperature patterns. As continents moved apart, new gateways formed between basins, while others were restricted or blocked. Warm equatorial waters could flow into some regions and not others, and cold currents began to trace different paths around the drifting landmasses. As a result, strong temperature gradients developed between shallow shelves and deeper basins, and zones of intense nutrient upwelling appeared where winds and currents interacted with new continental outlines. These changes produced a more varied and dynamic set of marine habitats than had existed around unified Pangaea. There were enclosed, warm interior seas, open ocean margins swept by currents, and broad epicontinental seaways that split continents in two. One of these, the future western interior seaway of North America, would later host dense populations of ammonites, fish, and other prey. In such rich, subdivided oceans, what kinds of predators would eventually rise to dominate these new marine worlds, and how would they adapt to hunt across this fractured blue planet? Millions of years before the first mosasaur entered the water, Earth's oceans were already changing into arenas of constant conflict. Imagine descending beneath a Jurassic Sea and finding not a quiet seafloor, but a landscape where almost every shell, tooth, and fin had been reshaped by attack and defense. This long interval, stretching from the early Jurassic into the Cretaceous, is known as the Mesozoic Marine Revolution. During this time, the balance of power in marine ecosystems began to shift. Earlier oceans had been dominated by relatively slow surface grazing and seafloor-dwelling organisms. Over time, however, predators that could crush, drill, or swiftly overtake their prey became more common. This process placed intense pressure on prey animals. As a result, the seafloor itself started to look different. Many clams, snails, and other shelled invertebrates responded by moving downward into the sediment. Burrowing forms became widespread, living hidden within the upper layers of the seafloor rather than exposed on top of it. Others thickened their shells, added spines, or developed shapes that made them harder to grasp. Because of this, any predator that hunted along the bottom had to become stronger, more precise, or more flexible in its feeding strategies. At the same time, life in the water column was changing as well. Teleost fishes, the group that includes most modern bony fish, diversified into faster and more agile swimmers. Their streamlined bodies, powerful tails, and improved control of buoyancy allowed them to dart, school, and accelerate away from danger. New prey such as coiled ammonites, with their chambered shells and complex patterns of motion, filled open marine habitats above the seafloor. Predators did not remain static in the face of these developments. Early sharks refined their teeth and swimming styles, while marine reptiles, such as ichthyosaurs and plesiosaurs, explored different hunting roles. Some became high-speed pursuit specialists with deep, crescent-shaped tails and large eyes for tracking moving targets. Others favored ambush, using long necks or broad bodies to launch sudden attacks from concealment. In many lineages, jaws became more powerful and more flexible, able to seize, slice, or crush a widening range of prey. These linked changes created an evolutionary arms race. Active, pursuit-based hunters with strong swimming abilities, sharp senses, and efficient lungs gained advantages in oceans where prey could flee, hide, or resist. In turn, prey animals that could burrow deeper, swim faster, or reinforce their shells were more likely to survive. The result was a more dynamic, three-dimensional marine world, from the shifting seafloor to the sunlit surface. Within this setting, marine reptiles diversified their feeding strategies. Some specialized in shell crushing, targeting thick-shelled clams and ammonites. Others focused on schooling teleost fishes, relying on speed and maneuverability. Still others combined scavenging with active hunting, following carcasses or patrolling coastal margins. Into these already competitive waters, another lineage was about to appear. Along the shorelines of the Cretaceous continents, certain lizards began to test the surf, taking the first tentative steps toward a new kind of ocean predator. Along those quiet Cretaceous shorelines, the story of the giant sea lizards began with bodies that were far more modest. Around 100 million years ago, small, monitor-like lizards moved along sandy bars, tidal flats, and estuaries at the edges of the continents. They hunted fish, crustaceans, and other small animals in the shallows, slipping into the water for short bursts before returning to the safety of the land. These early shore hunters still carried the basic design of a land lizard. Their limbs ended in clawed feet, their tails were only slightly flattened, and their ribs and vertebrae were built for walking rather than for continuous swimming. Over time, some lineages began to spend more and more of their lives along the water's edge. This process favored individuals that could hold their breath longer, push their bodies more efficiently through the water, and steer in currents and waves. Anatomical clues preserved in their bones show that these animals belonged to the squamates, the large reptile group that includes lizards and snakes. The structure of the skull, with loosely connected bones and a specialized joint at the back of the jaw, links them to modern monitor lizards and to snake-like forms. Certain features of the palate, the arrangement of teeth, and the way the vertebrae articulate all point to this shared ancestry. Because of this, Mosasaurs are often described as giant marine lizards, although their exact position among squamates remains under active debate. During this time, transitional species began to appear in coastal deposits. Their bodies became more elongated, with additional vertebrae in the trunk and tail. Limbs that once supported weight on land started to broaden and flatten, forming early paddle-like shapes. Joints stiffened, reducing the ability to walk, but improving the ability to sweep through water. As a result, these reptiles shifted from short, awkward swims to longer excursions into bays, lagoons, and eventually, the open margins of the Cretaceous seas. Fossils from Europe, the Middle East, and North America record this stepwise transformation. Some forms still had functional claws and could haul themselves onto the shore. Yet their tails were already tall and laterally compressed, acting as powerful rudders. Others show nearly complete flippers and reduced limb bones, signaling a life spent almost entirely off the land. In only a few million years, these changes accumulated, and the descendants of shore-hugging lizards became fully marine reptiles, capable of crossing broad seaways that separated the continents. The speed of this transition is striking when compared with the long history of Earth. How did such modest animals, living in the shadow of dinosaurs on land, so rapidly claim the role of apex predators offshore? Which specific anatomical changes turned a cautious shoreline hunter into a 50-foot ruler of the high seas, with a bite to challenge sharks and a range that spanned entire oceans? The next stage of their evolution begins to reveal the answer, but it also raises a deeper question about the limits of what a lizard's body can become. To understand those limits, it helps to build a sea dragon from the skeleton outward. A giant mosasaur did not resemble a stretched crocodile so much as a living torpedo. An elongated cylindrical torso, a deep, laterally compressed tail, and a head that formed a heavy blade-like prow. Its limbs, once suited for walking on land, had transformed into stiff, paddle-shaped flippers that acted less like engines and more like precise steering fins. In side view, the most striking feature was the tail. Near its end, the backbone bent sharply downward, supporting a tall, asymmetric fluke of soft tissue. This arrangement, inferred from fossils that preserve the outline of the tail, meant that most of the thrust came from powerful up and down strokes of the rear body, not from the forelimbs. Over time, vertebrae near the tail base became more robust and interlocking, forming a flexible yet stable beam that could transmit muscular force efficiently into the surrounding water. Bone histology offers an internal view of this process. When thin slices of mosasaur bones are examined under a microscope, they show dense, compact tissue in the limb elements and vertebrae, with patterns indicating strong, fast-twitch musculature was anchored there. Because of this, researchers interpret mosasaurs as active pursuit predators, closer in swimming style to sharks and ichthyosaurs than to slowly undulating marine crocodiles. Their streamlined bodies reduced drag, while the tail fluke allowed sudden bursts of speed and tight banking turns in the open ocean and in inland seaways. The skull reveals an equally radical re-engineering. Instead of a rigid, crushing head, mosasaurs carried flexible, kinetic skulls stitched together by mobile joints. The lower jaw was double-hinged. One joint connected it to the skull, while another mid-jaw joint allowed each half to bow outward. On the roof of the mouth, additional rows of pterygoid teeth formed a second gripping surface. When prey entered the mouth, these inner teeth could ratchet it backward, much like the feeding mechanism in snakes that would later share the ocean's surface only as much smaller animals on land. Their tooth shapes recorded what they hunted. Many species bore long, conical, sharply pointed teeth, ideal for piercing and holding slippery prey, such as fish and smaller marine reptiles. In other lineages, some teeth became shorter and more rounded, with thick enamel suited to cracking shells and armored bodies. During this time, the same basic mosasaur body plan supported both fast-moving pursuit specialists and slower crushing feeders that targeted hard-shelled ammonites and turtles. What did this combination of traits mean for Cretaceous seas? As a result, mosasaurs occupied the very top of the food web, filling roles that later oceans would assign to giant sharks like Otodus megalodon and the earliest large whales. In the western interior seaway that split North America, their remains appear alongside those of plesiosaurs and huge sea turtles, often with bite marks that show direct predation. These sea lizards had turned a once terrestrial frame into a highly tuned marine engine, and in doing so, they reshaped entire ecosystems. Yet this dominance was temporary. The same oceans that they ruled would soon be tested by one of the greatest crises in Earth's history, and their specialized design would face its final trial. Their dominance in these seas depended not only on power, but on perception. In the broad inland waters that formed as Pangaea broke apart, giant sea lizards moved through a sensory world very different from the sunlit shore. What did it mean to hunt in a column of dim blue water, where sound and pressure carried farther than light? Mosasaurs left no soft tissues of eyes or nerves, yet their skulls preserve important clues. Many species show large, forward-facing eye sockets, sometimes braced by bony scleral rings similar to those in birds and some reptiles today. This arrangement suggests relatively large eyes held rigid against water pressure, adapted to mid-depth zones where daylight still penetrated but was already filtered to a blue-green gloom. During this time, the western interior seaway would have offered broad shelves of such water, and mosasaurs appear to have occupied that band with precision. Vision alone, however, could not explain their success. Inside the dense rock of their skulls, the cavities for the inner ear are enlarged and shaped in ways that indicate sensitivity to vibration and possibly low-frequency sound. This process of detecting pressure changes would have allowed them to sense the movement of shoaling fish, the flutter of a diving bird's wings, or the thrash of a wounded reptile long before it came into view. Over time, as these predators spread across the Cretaceous oceans, such heightened awareness turned the seaway into an acoustic hunting ground. With these senses, mosasaurs employed a range of strategies. Some, with deep chests and powerful tails, were built for short bursts of high speed, rising from below in sudden ambushes that used the contrast between dark depths and brighter surface to hide their approach. Others, more streamlined, likely engaged in open water chases, pacing schools of fish or ammonites before lunging through them. Because of this flexibility, the same lineage could exploit reefs, open shelves, and nearshore channels, tracking seasonal migrations, much as later marine predators would do. Fossils provide direct snapshots of these encounters. Stomach contents of large Tylosaurus individuals from the interior of North America preserve bones of diving birds, small mosasaurs, fish, and even fragments of large sea turtles. Bite-marked plesiosaur vertebrae and damaged ammonite shells show powerful jaws closing on hard, spinning targets. As a result, a picture emerges of opportunistic hunters that tested almost any available prey, from delicate wing bones to armored carapaces, and swallowed them with double-hinged jaws and backward-pointing teeth. Imagine, then, the sensory world from the other side. A small fish drifts over the chalky seafloor of the western interior seaway, where sediments from distant continents slowly settle through still water. The light is soft, filtered through a broad, shallow sea. There is no warning at first, only a deep, low-frequency pulse and a slight change in pressure as something vast displaces the water below. A shadow thickens, the blue turns briefly to darkness, and a jaw lined with interlocking teeth rises from the gloom, closing the distance in a single, final rush. For a moment, the rushing jaws fill the entire field of vision. Then the scene pulls back, and that single predator becomes just one inhabitant of a much larger stage. During this time in Earth's history, the heart of a continent was not solid ground at all. It was ocean. In the late Cretaceous, North America was split from north to south by a vast inland sea known as the Western Interior Seaway. High global sea levels, driven by rapid seafloor spreading and the heat released from the mantle, raised the world's oceans. At the same time, parts of the continental crust in the interior slowly sagged under the weight of nearby mountain building. As a result, warm, shallow water advanced from the Arctic in the north and from the ancestral Gulf of Mexico in the south until the two arms met across the center of the continent. This inland sea formed in a very specific tectonic setting. To the west, the early Rocky Mountain region was beginning to rise as an oceanic plate slid shallowly beneath the continent, crumpling and thickening the crust. To the east, the ancient, stable Craton of North America remained relatively low and rigid. Between these two contrasting regions, the surface flexed downward. Over time, this flexure created a long, narrow marine corridor that could be hundreds of kilometers wide, yet remained connected to global oceans at both ends. Within the Western Interior Seaway, conditions were far from uniform. The central axis of the basin held deeper channels, where darker, quieter waters accumulated fine muds and preserved delicate shells and bones. Broad sunlit shelves spread out toward the margins, forming extensive shallow platforms where carbonate sediments formed and schools of fish and invertebrates thrived. Along the shifting shorelines, river systems built wide coastal deltas, carrying sediment from the rising highlands into the sea. offshore islands, formed from older blocks of crust, stood as low ridges where forests and nesting grounds developed. Each of these settings supported its own communities of marine reptiles, fish, ammonites, and plankton. The Western Interior Seaway was not an isolated curiosity. It was one outcome of the long breakup of Pangaea and the greenhouse climate that followed. As continents drifted apart, new ocean basins formed, mid-ocean ridges lengthened, and the total volume of hot, buoyant crust beneath the oceans increased. Because of this, sea level rose across the planet, and low-lying continental interiors were flooded. This process created other epicontinental seas around the world, but few were as extensive or as well preserved in the rock record as the seaway that split North America. In this flooded corridor, stretching from polar latitudes to the subtropics, which marine reptiles would claim the highest ranks of the food chain? How would long-necked plesiosaurs, massive sea turtles, early birds, and the rising lineage of giant sea lizards divide this inland ocean? And what happened when their hunting grounds overlapped? In the heart of that inland ocean, one lineage of reptiles rose above all others. Among them, Tylosaurus stood out as one of the largest and most formidable hunters the Western Interior Seaway ever produced. Some individuals stretched more than 12 to 14 meters from snout to tail. With a deep, muscular body, a powerful tail fin, and a robust skull that ended in a long, reinforced snout like a living battering ram. Fossils from the chalk beds of Kansas and neighboring regions preserve more than just its bones. They preserve its appetite. Within the rib cages of Tylosaurus skeletons, paleontologists have found the remains of large fish, diving birds, fragments of turtles, pieces of long-necked plesiosaurs, and even the skeletons of smaller mosasaurs. During this time, the top predator of the seaway was not a shark or a pliosaur, but a giant sea lizard that treated almost any other swimmer as potential prey. As a result, Tylosaurus is understood as a true apex predator, occupying the highest tier of its marine food web. Yet the Western Interior Seaway did not belong to Tylosaurus alone. Other mosasaurs shared these waters, each shaped by evolution into slightly different roles. Platecarpus, for example, was shorter and more streamlined, with a more flexible neck and teeth, suited to seizing fish and squid-like animals. Cleidasts, smaller and more agile, had a relatively narrow skull and sharp, piercing teeth that suggest a focus on smaller, fast-moving prey near the surface. Over time, differences in body size, skull shape, and tooth form reduced direct competition and allowed several mosasaur genera to coexist. Seen together, these reptiles formed only part of a dense and complex food web. Schools of bony fish and shimmering shoals of smaller predators filled the water column. Ammonites drifted and swam in spiraling shells, while great sea turtles cruised between nesting beaches on the distant continents. Long-necked plesiosaurs hunted with sweeping arcs of their heads, and diving birds plunged from the air, folding their wings as they cut through the surface. Among them moved multiple mosasaur species, rising to breathe, diving again, and patrolling different depths and regions of the seaway. Then comes an apparent paradox. With so many large predators sharing the same waters, why did they not simply overhunt their prey and wipe each other out? This process of coexistence depended on subtle differences in diet, hunting strategy, and preferred habitat, from open ocean channels to shallower coastal shelves. Because of this, the Western Interior Seaway functioned less like a single battleground and more like a mosaic of overlapping territories, setting the stage for further specializations and new evolutionary experiments in the Cretaceous seas. In the late Cretaceous, the inland seas that split the continents did not hold a single dominant hunter, but an entire community of giants. Imagine looking across the Western Interior Seaway and knowing that beneath every wave, several different predators were sharing the same water without driving each other to immediate extinction. How could so many large carnivores survive in one connected basin? The answer lies in ecological niches. Even when animals seem similar on the surface, this process of partitioning allows them to specialize in different prey, depths, or parts of the habitat. During this time, mosasaurs diversified into a remarkable range of forms. Slender, streamlined species with narrow, blade-like teeth focused on fish and squid, chasing schools through the midwater column. Heavier, deep-jawed species carried robust skulls and thicker teeth, suited to seizing larger vertebrates such as other reptiles or big bony fish. As a result, predators that might appear to be direct competitors instead concentrated on different slices of the available resources. One of the clearest examples comes from Durophagous mosasaurs, such as globidins. Its short, rounded teeth were not designed to slice flesh, but to crush. With a powerful bite and reinforced jaws, it targeted hard-shelled prey, from ammonites to large clams that lived on or near the seafloor. Over time, such specializations reduced direct overlap with the fast, fish-hunting mosasaurs above, and with the more generalist, large prey hunters that patrolled open channels of the seaway. Mosasaurs also shared these waters with other marine reptiles whose bodies reflected different roles. Long-necked plesiosaurs, with small heads and numerous fine teeth, were suited to picking smaller, agile prey, perhaps in quieter coastal zones or near the surface where schools gathered. Short-necked pliosaurs, when still present in some regions, carried massive skulls and large conical teeth, focusing on larger struggling animals in more open water. Giant marine turtles, protected by broad shells and equipped with beaks rather than teeth, likely grazed on seafloor vegetation or tore at soft invertebrates, occupying yet another niche within the same system. Evidence for this partitioning is preserved in the fossils themselves. Toothwear patterns on globidins and related forms show pitted, abraded enamel, consistent with cracking shells rather than slicing flesh. In contrast, the fine, serrated teeth of some mosasaurs show microscopic scratches typical of cutting softer prey. Jaw mechanics reconstructed from skull bones indicate differing bite forces and gape, matching predictions for crushing, gripping, or rapid snapping. Even the geographic and stratigraphic distribution of these animals suggests separation, with certain species more common in deeper central channels and others clustered along shallower continental shelves. Because of this, the Cretaceous seas were not a chaotic free-for-all, but a structured web of interactions shaped by anatomy, behavior, and environment. Yet, even as mosasaurs rose to dominate many of these roles, they entered ecosystems already shaped by earlier marine reptiles. They were not the first rulers of the oceans, and they were not alone. The next chapter of this history follows how these lizards expanded into spaces once held by older lineages, and how that balance would be tested at the very end of the Cretaceous. As mosasaurs spread through the Cretaceous seas, they entered waters already patrolled by very different reptiles. Long before these lizards appeared, plesiosaurs and their close relatives, the pliosaurs, had formed a parallel maritime empire. Their bodies, their swimming styles, and even their preferred prey created a striking contrast that shaped how life in these oceans was organized. Classic plesiosaurs, such as Elasmosaurus, are among the most distinctive reptiles in Earth's history. Their bodies carried extremely long necks with dozens of vertebrae, supporting relatively small heads armed with slender interlocking teeth. When these animals moved through inland seas, like the Western Interior Seaway, the main body could remain deeper, while the neck swept quietly through schools of small fish and cephalopods. This process likely allowed them to approach prey with minimal disturbance at the surface, striking with quick sideways motions rather than high-speed chases. Pliosaurs represented the other end of this lineage. They had short, muscular necks, massive skulls, and deep jaws designed for powerful bites at close range. Many of the largest forms peaked earlier during the Jurassic. Yet some pliosaurs continued into the Cretaceous and still occupied important roles. Instead of selective feeding on small animals, their anatomy indicates an ability to seize sizable prey, including large fish, other marine reptiles, and perhaps even young individuals of their own kind. Over time, these different skull and neck proportions created a spectrum of hunting strategies within the same broader group. Both plesiosaurs and pliosaurs moved through the water using 4 strong flippers. Each limb acted like a hydrofoil, generating lift and thrust in a motion sometimes compared to underwater flight. The front and rear pairs could beat in slightly different patterns, helping with acceleration, braking, and sharp turns. Because of this limb-driven propulsion, these reptiles likely had excellent maneuverability at moderate speeds, especially in shallower seas and along continental margins where sudden changes in direction were valuable. Mosasaurs, by contrast, relied on tail-powered swimming. Their elongated bodies and deep tail fins produced rapid side-to-side waves, driving them forward or more like sharks. This difference in propulsion suggests that mosasaurs often excelled at bursts of speed and long-distance cruising, while plesiosaurs and pliosaurs favored precision movement and hovering control. During this time, all 3 groups shared the same broad ocean basins, but partitioned them by depth, prey size, and hunting style. In some regions, long-necked plesiosaurs likely focused on small, agile prey near the upper water column, while pliosaurs and larger mosasaurs targeted heavier animals in deeper or more open zones. Bite marks on bones, preserved stomach contents, and the distribution of fossils across former continents indicate partial overlap, but not complete competition. Yet a question remains. If plesiosaurs had ruled the seas for so long, what sequence of changes allowed the relatively late-arriving mosasaurs to overtake them in many ecosystems? And why did that advantage matter when the Cretaceous drew to a sudden close? To answer that, it helps to remember that mosasaurs entered oceans already crowded with older lineages. Long before their rise, another group of marine reptiles had ruled the planet's seas, the ichthyosaurs. During this time, they were so successful that in many Jurassic oceans, almost every major open water niche was filled by some streamlined, fish-shaped form. Ichthyosaurs had evolved from land reptiles much earlier in Mesozoic history, but their bodies became highly specialized for life in the water. They developed smooth, torpedo-shaped outlines, crescent tails, and stiff, paddle-like limbs that acted as stabilizers rather than walking limbs. Many species possessed very large eyes, supported by bony rings, an adaptation that likely improved vision in dim, deep water or during crepuscular hunting. Fossil skeletons with embryos preserved inside the body show that they gave birth to live young at sea, so they did not need to return to land in the way early turtles and some other reptiles did. By the early Cretaceous, however, this long dominance was fading. Ichthyosaurs still cruised the oceans, but their diversity had begun to decline. Over time, entire lineages disappeared, and by roughly the mid-Cretaceous, they were gone, vanishing before mosasaurs reached their peak. Why did such efficient predators fail in oceans that still supported large reptiles, sharks, and fish? This remains an active question in marine paleontology. Several hypotheses have been proposed. Some scientists suggest ecological competition, perhaps from rapidly diversifying teleost fishes or from other marine reptiles that targeted similar prey. Others emphasize environmental change, shifting sea levels, altered ocean circulation, and changing climate patterns as continents moved and seaways opened and closed. A third idea focuses on prey availability. If the specific squid-like animals and fish that many ichthyosaurs specialized on declined or shifted range, this process could have left them vulnerable. As a result, a group that once seemed nearly invincible disappeared, leaving ecological space that later groups, including mosasaurs, could exploit. Not every old lineage vanished. Another branch of marine reptiles, the sea turtles, continued and expanded. In the late Cretaceous, giants such as Archelon inhabited broad epicontinental seas like the western interior seaway that split North America. Archelon reached lengths of more than 4 meters, with flippers spanning even farther, and had a leathery, partially reduced shell rather than a rigid dome. Its overall role appears somewhat analogous to modern leatherback turtles, likely cruising long distances and feeding on soft-bodied prey. Here, the pattern changes sharply. Instead of being the top hunters, these giant turtles often shared waters with large mosasaurs. In some regions, Archelon and its relatives probably competed with mosasaurs and certain fishes for jellyfish, cephalopods, or other soft prey. In other cases, they almost certainly became prey themselves. Bite marks on turtle shells and the presence of turtle remains within mosasaur-rich deposits suggest direct predation. The same seas that allowed turtles to reach impressive sizes also held reptiles capable of attacking them. Seen together, ichthyosaurs in decline and giant turtles in their prime show that Cretaceous oceans were not defined by a single group. They were layered, evolving ecosystems with deep roots in earlier marine reptile history, shaped by shifting continents and changing climate. The rise of mosasaurs occurred within this complex setting, not outside it, and the next step is to examine how their own anatomy and behavior turned them into some of the most formidable hunters Earth's oceans have ever hosted. The oceans that hosted the great sea lizards did not exist in isolation. They were part of a planet locked in one of the warmest chapters of its recent history. During this time in the late Cretaceous, Earth was a greenhouse world. Global temperatures were higher, atmospheric carbon dioxide was elevated, and there was little to no permanent ice at the poles. As a result, more of the planet's water was held in the oceans rather than trapped in ice, and sea level rose to flood the edges of continents. This flooded state reshaped the map of the surface. Low-lying regions of the crust that are dry land today were covered by shallow seas. The western interior seaway stretched from what is now the Arctic Ocean to the Gulf of Mexico, splitting North America into separate landmasses. Similar epicontinental seas spread across parts of Europe and Africa. These broad sunlit shelves formed vast habitats where marine reptiles, including mosasaurs, plesiosaurs, and large sea turtles, could feed, migrate, and diversify. The climate itself was not only warm but relatively stable. Tropical and subtropical conditions extended far toward the poles. In regions that now experience freezing winters, warm waters washed over coastal plains and inland basins. Because of this, marine reptiles were able to inhabit higher latitudes than many modern reptiles can tolerate. Fossils of mosasaurs and other marine reptiles occur in areas that are now temperate or even subpolar, showing that these animals followed the warmth as it spread away from the equator. Ocean circulation under greenhouse conditions also differed from that of the present day. Warm surface waters and denser, cooler deep waters often formed distinct layers, leading to stratified seas. In some basins, limited mixing allowed oxygen levels at depth to fall, creating oxygen poor zones on the seafloor. This process restricted where large predators could hunt and where their prey could safely live. In well-ventilated regions, such as open connections between major basins and along active continental margins, oxygen-rich waters supported dense food webs that could sustain giant carnivores. Within the shallow epicontinental seas, conditions were especially favorable. Sunlight penetrated to the seafloor, fueling plankton blooms and productive ecosystems from the bottom up. Over time, this productivity built thick layers of organic-rich sediment that still record the chemistry of those waters. For mosasaurs, these environments offered extensive coastlines, island chains, and interior passages to exploit, turning flooded continents into networks of hunting grounds. In this greenhouse world of high seas and warm currents, the stage was set. Vast inland oceans, stratified basins, and poleward-reaching subtropical belts created a mosaic of opportunities and barriers. Against this backdrop, what did daily existence look like for a giant sea lizard moving through these ancient waters? The answer lies in the details of their bodies, their movement, and their hunting strategies beneath the Cretaceous waves. In the pale light of an early Cretaceous dawn, the western interior seaway is quiet at the surface, but far below, a giant is already moving. A large Tylosaurus, more than 12 meters from snout to tail, begins to rise from deeper, cooler layers of water. Its lungs must be refilled, but another need drives this ascent as well. The warmth near the surface helps stabilize its body temperature and keeps its muscles ready for sudden bursts of effort. When it breaks the surface, the event is brief and controlled. A rush of exhaled air, a fresh breath drawn in, and then the body tilts down again, slipping back beneath the waves. Over time, this repeated movement between depths allows the animal to balance energy use with the demands of hunting. Sunlight filters down through the upper layer, tracing patterns along its dark back and paler underside, a form of counter-shading that makes the predator harder to detect from above or below. As the morning brightens, the Tylosaurus settles into a slow patrol along a submerged ridge, the drowned edge of an ancient reef system that once lay near the margin of Cretaceous continents. Here, the seafloor rises in steps and ledges. Shoals of fish cluster along the top of the ridge. Ammonites drift in the open water just beyond, their coiled shells catching the light. Above, the silhouettes of diving birds and smaller marine reptiles briefly pierce the surface, then vanish again into the water column. This environment concentrates life, and this process concentrates opportunity. Jaw joints and neck vertebrae allow the mosasaur to make fine adjustments as it scans. Its tail, deep and finned like that of a shark, provides slow, economical strokes while it watches for weakness at the edges of the schools. Stomach contents from related species show fish, ammonites, and even fragments of diving birds. So this range of targets is not theoretical. It is recorded in the rock. The strike, when it comes, is sudden. A school of mid-sized fish shifts direction a fraction too late. The Tylosaurus accelerates with a powerful series of tail beats, closing the distance in seconds. Its blunt snout, reinforced with dense bone, slams into the side of the cluster, stunning and scattering prey. As a result, individual fish are separated from the main group. Double-hinged jaws open wide, recurved teeth snap shut, and the predator bites, releases, and repositions, working the body of a larger fish headfirst down its throat, so fins will fold rather than catch. During this time, the mosasaur is not alone in its domain. The sound and motion draw smaller fish that circle near its flanks, picking at loose scales and fragments. Farther along the ridge, chemical traces in the water lead it toward a drifting carcass, perhaps a dead plesiosaur. The Tylosaurus feeds cautiously, tearing away sections of flesh, but veers off when the outline of another large mosasaur appears in the haze. Territories are not marked on any map, yet repeated encounters and injuries over time have created invisible boundaries in this inland sea. As the sun lowers and the surface waters begin to lose heat, the Tylosaurus descends again, following cooler, denser layers into dimmer zones where its eyes still function, but colors fade. The daily circuit of rising, patrolling, striking, and retreating has unfolded countless times across millions of years on this planet. What other strategies, rivalries, and hidden behaviors filled these ancient oceans? And how can the fragments preserved in Earth's crust reveal them more clearly in the next part of this story? To understand those hidden behaviors more clearly, it is necessary to step back from the adult hunter and consider how such giants began. Every apex predator in the Cretaceous seas started life as something small, soft-boned, and uncertain. The life cycle of mosasaurs, from embryo to enormous hunter, shaped how these reptiles spread through the inland seaways that covered large parts of Earth's surface during this time. Evidence from fossils indicates that mosasaurs did not return to land to bury eggs in the crust of ancient beaches. Instead, like several other marine reptiles, they likely gave birth to live young at sea. Tiny articulated skeletons, preserved inside or close to the body cavities of larger individuals, show proportions consistent with embryos rather than prey. In addition, the structure of the pelvis and hind limbs in many species seems poorly suited for hauling the body onto shore. As a result, reproduction appears to have been fully adapted to open water. If birth occurred at sea, where did the smallest mosasaurs spend their early months? Geological and fossil evidence suggests that protected coastal embayments and shallow zones of inland seaways functioned as nurseries. In formations laid down by the western interior seaway, for example, layers rich in small mosasaur bones and teeth occur alongside fossils of gentle-shelved shorelines, fine muds, and abundant small fish and invertebrates. This combination points to quiet, food-rich environments where wave energy was lower and the largest predators were less frequent visitors. Within these nurseries, growth needed to be rapid. Bone histology from different mosasaur species reveals dense networks of growth lines and relatively porous internal textures, a pattern associated with high metabolic rates and fast size increase. During this time, juveniles may have moved quickly through vulnerable size classes, shifting their diets as jaws and teeth strengthened. Over time, their ecological role changed from small fish and invertebrate hunters to mid-level predators, and finally, to the massive forms that rivaled sharks for dominance. Parental behavior remains harder to reconstruct. Modern squamates, the broader group that includes lizards and snakes, show a wide range of strategies, from abandoning eggs immediately to guarding nests or remaining near hatchlings for a short period. Because of this diversity, direct analogies are uncertain. However, if mosasaurs did concentrate births in sheltered nursery regions, the repeated use of such habitats might indicate at least some spatial protection, even if active guarding was limited. This process would have created zones where generations overlapped, with subadults sharing space with the newest arrivals. Here, a quiet interruption of scale is useful. The immense skull of a 15-meter Mosasaurus, resting today in a museum drawer, or locked in Earth's mantle-derived rocks, once belonged to an animal that began as a fragile, half-meter newborn. It entered a sea filled with larger predators, sudden storms, and even cannibalistic relatives. Every tooth-marked jaw and shattered vertebra from a giant mosasaur carries that hidden beginning, a tiny swimmer pushing through the first waves of a dangerous planet-wide ocean. Every shattered jaw and scattered vertebra from these seas is more than a record of death. It is also a record of behavior. In the absence of living witnesses, paleontologists turn to teeth, bones, and rare traces of soft tissue to reconstruct how these giant sea lizards hunted, fed, and moved through the Cretaceous oceans. Teeth offer one of the clearest starting points. Slender, sharply pointed teeth with smooth enamel and fine microscopic scratches along their length indicate a diet of soft-bodied prey, such as fish and squid, seized and swallowed with minimal resistance. In contrast, blunt, heavy-crowned teeth with thickened enamel and crushed, spalled tips belong to shell crushers that attacked ammonites and turtles, breaking hard armor through repeated biting. Between these extremes stand generalist predators, with robust, slightly curved teeth that show mixed wear patterns, suggesting a flexible feeding style that shifted as prey communities changed over time. Under a microscope, the tooth surfaces become a landscape of behavior. Parallel scratches record the direction of jaw motion, while cross-cutting pits and gouges reveal sudden impacts with bone or shell. During this time, some mosasaurs evolved deeply rooted conical teeth with reinforced bases, a design that reduced breakage when they clamped onto struggling prey. As a result, their skulls functioned as dynamic tools, shaped by both evolutionary history and daily feeding. Occasionally, the record is even more direct. Several famous skeletons preserve the remains of last meals, trapped within the ribcage. One large mosasaur from the western interior seaway contains articulated fish vertebrae and fin spines, showing that it swallowed sizable prey nearly whole. Another specimen preserves the bones of a diving bird, evidence that these reptiles attacked from below, turning the boundary between air and water into an ambush zone. In rare cases, the stomach region holds the partial skeleton of a smaller mosasaur, indicating that cannibalism was not only possible, but sometimes practiced. Bones from other marine reptiles also carry the signatures of attack and encounter. Turtle shells and plesiosaur ribs from Cretaceous seafloor deposits often bear U-shaped arcs of punctures that match mosasaur tooth spacing with striking precision. Some marks show healing, meaning the victim survived an encounter. Others are associated with disarticulated carcasses, suggesting scavenging on bodies that had already sunk to the seafloor. Intraspecific combat is recorded as well in mosasaur skulls with healed bite marks along the snout and jaws, hinting at territorial fights or dominance contests in crowded coastal corridors. Even the outline of the body can sometimes be read from stone. Exceptional fossils preserve impressions of scaly skin, showing small overlapping scales that covered much of the surface, rather than the smooth hide often imagined. Other specimens reveal a deep, downward bent tail with a soft tissue fluke, similar in profile to that of a shark. This process of comparing tail shape, muscle attachment scars, and hydrodynamic models demonstrates that the power stroke came from the tail, while the limbs acted more as stabilizers than primary propellers. Taken together, these traces form a dense archive of behavior. Teeth record diet, bite marks reveal conflict and predation, and soft tissue impressions refine the outline of the living animal. Yet another question remains. With such a rich fossil record, can these same bones and teeth show not only how this oceanic empire functioned, but how it finally collapsed at the end of the Cretaceous? Yet those bones and teeth do more than record collapse. They also trace a remarkable rise. Around 100 million years ago, during the middle of the Cretaceous, the oceans of Earth began to shift from older reptile dynasties to a new kind of hunter. Small semi-aquatic lizards, probably related to early monitor lizards and snakes, first adapted to life along the shoreline, then ventured farther from land. Over time, these modest coastal predators lengthened their bodies, strengthened their tails, and reshaped their limbs into powerful flippers. By about 90 million years ago, the first true mosasaurs had formed, already capable of active pursuit in open water. During this time, their skeletons show a rapid series of changes. Vertebrae became more flexible, tails developed deep flukes, and skulls evolved double-hinged joints that allowed them to swallow large prey. This rise did not happen in an empty ocean. Earlier in the Mesozoic, ichthyosaurs had dominated many marine habitats, while large pliosaurs had filled the role of massive short-necked predators. As the Cretaceous advanced, ichthyosaurs declined and finally vanished, and several pliosaur lineages also disappeared. Because of this, major ecological spaces were left unoccupied. Large, fast-moving prey remained, but the traditional hunters were gone. Mosasaurs expanded into these openings with remarkable speed. This process can be traced in rock layers from Europe, North America, Africa, and New Zealand, where successive species appear larger, more specialized, and more widespread. Some forms developed robust, crushing teeth for hard-shelled ammonites and turtles. Others evolved slender, blade-like teeth for slicing soft-bodied prey. A few even show adaptations for hunting other marine reptiles, including their own relatives. As a result, mosasaurs came to occupy nearly every major predatory niche in the late Cretaceous seas. Global geography strongly supported this expansion. The breakup of earlier continents and the long separation after Pangaea meant that high sea levels flooded the margins of many landmasses. Warm, shallow seaways spread across the planet's surface, including the broad western interior seaway that split North America. During this time, sunlight penetrated to the seafloor over wide areas, fueling rich plankton blooms and complex food webs. Active, air-breathing reptiles that could cruise long distances and surface quickly for air were favored in these environments. By the final 20 million years of the Cretaceous, Mosasaurs had reached peak diversity. Small streamlined species hunted fish near coasts, mid-sized forms patrolled continental shelves, and giants over 15 meters long ruled the open ocean. Their flexible body plan, rapid growth, and varied feeding strategies allowed them to spread across many seas and between distant continents. With such dominance and adaptability, what could disturb this oceanic empire? What event could remove predators that had filled nearly every role available? The answer would not come from a rival reptile, but from far beyond the waves and from deep within the planet's own history. Dominance in the oceans did not mean stability. Even before the final catastrophe at the end of the Cretaceous, Earth's systems were already shifting beneath the waves. The giant sea lizards hunted in seas that were changing in level, temperature, and chemistry, and these gradual adjustments began to place quiet pressure on the communities that supported them. During this time, global sea level reached some of the highest points in Earth's history, flooding low areas of the continents and forming broad inland seaways. Over time, however, sea level did not remain fixed. Subtle changes in the rate of seafloor spreading, the volume of mid-ocean ridges, and the growth of mountain belts on the continents caused coastlines to advance and retreat. As shorelines migrated, shallow marine habitats expanded in some regions and shrank in others, altering nurseries for fish, ammonites, and the smaller reptiles that fed young mosasaurs. Evidence from fossil shells and seafloor sediments shows that ocean chemistry was also in flux. Isotopes of oxygen and carbon preserved in microscopic plankton skeletons. Record cooling trends in some high-latitude regions late in the Cretaceous. At the same time, changes in nutrient delivery from rivers and from upwelling deep waters altered plankton communities. Because of this, the base of the food web shifted in composition and productivity. This process could favor certain plankton groups while disadvantaging others, reshaping which organisms thrived in surface waters and which sank to feed deep ecosystems. As a result, marine reptiles did not all respond in the same way. Some plesiosaurs, especially the long-necked forms that had flourished in earlier intervals, show a decline in diversity toward the latest Cretaceous. Their fossils become rarer in many basins, and their range appears to contract. In contrast, mosasaurs remained taxonomically diverse and occupied many ecological roles, from deep-diving predators to shell crushers in coastal zones. Yet even they were not uniform in their success. Certain regions show signs of stress in local mosasaur faunas, suggesting that particular seaways or climate belts may have become less favorable, while others still supported rich populations. Beneath the crust, deeper forces were also at work. In what is now India, huge volcanic eruptions began to build the Deccan Traps, releasing large volumes of gases into the atmosphere. Over time, pulses of carbon dioxide could warm some parts of the planet, while sulfur-rich aerosols might briefly cool the surface and disturb rainfall patterns. Repeated episodes of eruption, gas release, and climate disturbance would have affected ocean circulation and oxygen levels, adding long-term environmental pressure on already shifting marine ecosystems. Here, the pattern interrupts the apparent security of apex predators. A giant mosasaur depended on dense schools of fish, on thriving ammonites, and on plankton blooms that sustained the entire chain. Even the largest hunter was only as secure as the food webs beneath it, and those webs were about to face their ultimate test. Those food webs reached their breaking point on a single day. 66 million years ago, near what is now the Yucatan Peninsula, a roughly 10-kilometer-wide asteroid entered Earth's atmosphere and struck shallow tropical seas. In a fraction of a second, the rock that formed the local crust was compressed, melted, and blasted aside, excavating the vast structure now known as the Chicxulub crater. For marine reptiles ruling nearby waters, the horizon itself became lethal. When the asteroid hit, energy was released on a scale far beyond any volcanic eruption in recent history. Water and seafloor sediment were displaced outward in a towering ring. Mega tsunamis raced away from the impact site, crossing ocean basins and invading coastlines. Along continental margins and inland seaways, walls of water scoured shorelines, overturned habitats, and hurled marine reptiles, fish, and ammonites into turbulent, debris-filled flows. Shallow shelves that had formed stable hunting grounds for mosasaurs and plesiosaurs were suddenly ripped apart. Shock waves moved through the ocean and through the solid earth. Seafloor slopes failed and collapsed, releasing underwater landslides that generated additional tsunamis. In some regions, the water column would have been filled with suspended mud, broken shells, and shattered carbonate from the disturbed crust. During this time, visibility dropped to almost nothing. Sound fields were chaotic, and many animals died not from direct impact, but from being buried, battered, or stranded as sea levels temporarily surged and retreated. Above the surface, the impact vaporized enormous volumes of rock and sulfate-rich sediments. Dust, sulfur aerosols, and droplets of molten material were thrown high into the atmosphere and spread around the planet. As this material encircled Earth, it blocked and scattered sunlight. Over time, daylight dimmed to a twilight gloom, even far from the impact basin. This process drove a rapid decline in temperatures at the surface and in the upper ocean, creating a short, intense impact winter. Because of this sudden reduction in light, photosynthesis faltered on land and in the sea. Microscopic plankton that had formed the base of Cretaceous marine food webs could no longer grow at former rates. Their populations collapsed in many regions. As a result, everything that depended on them began to face starvation. Small filter-feeding organisms declined, then the fish that preyed on them, and finally, the large predators that hunted those fish, including the giant mosasaurs that had recently dominated inland seas. What did it mean for an apex hunter when the pyramid beneath it simply vanished? Even individuals that survived the initial tsunamis now swam in oceans where each hunting trip yielded less energy than the one before. In the darkened, cooling seas that followed, only lineages with particular traits, such as flexible diets, small body sizes, or slow metabolisms, had a chance to endure. Others, including many great marine reptiles, were doomed within a geological blink. Which branches of this ancient marine empire would persist into the next era, and which would disappear forever? In the fading light of the Cretaceous seas, the fate of the mosasaurs was sealed by the very traits that had once made them dominant. These reptiles were large, fast-growing apex predators, and their bodies demanded a constant flow of energy. To sustain such size and power, they relied on abundant prey, schools of mid-sized fish, flocks of marine birds, ammonites, and even other reptiles. When that prey base faltered, their entire way of life became unstable. After the impact, food webs in the oceans did not simply weaken. They fractured. Plankton populations collapsed, and with them the small fish and invertebrates that formed the base of the marine pyramid. As a result, the mid to large-sized animals that mosasaurs hunted became scarce or vanished from entire regions. A predator that needed to consume large, energy-rich meals now faced long, empty stretches of sea. Hunting trips that had once been efficient began to cost more energy than they returned. Their fully marine, air-breathing lifestyle increased this vulnerability. Mosasaurs had evolved away from the shore, with limbs transformed into flippers and tails shaped into powerful, finned propellers. During this time, the broad epicontinental seas, created by the breakup of earlier continents, had been ideal habitats, After the impact, these same shallow basins became zones of chaos. Tsunamis raced across continental shelves, sediment slumps buried seafloor communities, and coastal ecosystems were stripped or poisoned. Unlike some semi-aquatic reptiles, mosasaurs had few refuges. They could not retreat deep into burrows, nor could they easily shift into small rivers, lakes, or isolated lagoons that might have retained pockets of life. Their need to surface for air tied them to an ocean surface choked with debris, fluctuating temperatures, and rapidly changing chemistry. Because of this, each journey to breathe also brought them into a disrupted, resource-poor environment. In contrast, smaller and more generalist organisms were better suited to survive this process of collapse. Some fish and invertebrates could subsist on detritus falling from the upper waters, or switch among different food sources as conditions changed. Birds with strong flight and flexible diets could move between marine and coastal habitats, exploiting patchy resources. Small reptiles, including some that would later give rise to modern marine lineages, could hide in sheltered environments and endure long periods of scarcity. Plesiosaurs and many other large marine reptiles shared the mosasaurs' fate. Long-necked forms that had once hunted in the same inland seas, and robust, short-necked predators that rivaled mosasaurs in power, also disappeared. With their loss, a long era of reptilian dominance in the open oceans, stretching back to the early Mesozoic, came to an end. What would take their place? As Earth's oceans slowly recovered, new groups began to explore the vacant hunting grounds left behind by the giant sea lizards. In time, entirely different kinds of animals would rise to claim those thrones, reshaping life in the seas in ways that would echo across the rest of the planet. In the first moments after the extinction, the seas that had once carried mosasaurs were strangely quiet. Plankton communities crashed, food webs broke apart, and many coastal shelves that had supported dense life became biological deserts. During this time, the oceans did not lose their tides or their currents, but they briefly lost much of their complexity. Apex predators were gone, and even many of their prey had vanished. Over time, surviving lineages began to rebuild these damaged systems. Tiny plankton radiated into new forms, feeding small invertebrates that in turn supported recovering fish populations. Coral and shell-forming organisms slowly reappeared on the seafloor. This process of ecological succession allowed energy to move through the water column again. Because of this gradual rebuilding, vacant ecological roles opened across the oceans, ready to be filled by new hunters. Among the first to expand were sharks and teleost fishes. Sharks that had once shared the seas with mosasaurs now faced far less competition. Their teeth, skeletons, and swimming styles diversified as different lineages explored new diets and depths. Teleost fishes with flexible jaws and efficient swimming also radiated into reefs, open waters, and deep pelagic zones. As a result, some shark groups evolved into large macropredators that would, much later, produce giants such as megalodon, taking over apex roles once held by the giant sea lizards. At the same time, on land, small hoofed mammals living along ancient shorelines began to edge into the water. Early in this history, some waded in shallow lagoons, feeding on plants or small animals along the bottom. Later descendants became stronger swimmers, lengthening their bodies, reshaping their limbs, and developing more powerful tails. Over tens of millions of years, these experiments produced fully aquatic whales, from early archaeocetes with hind limbs to streamlined forms that never again walked on the continents. Their story parallels that of mosasaurs, but remains distinct. Both groups began as land-dwelling reptiles or mammals, and then shifted into coastal shallows before mastering the open ocean. In each case, natural selection favored similar solutions: elongated, hydrodynamic bodies, strong tail-driven propulsion, and senses tuned to tracking prey through three-dimensional space. Large predatory whales and later giant sharks thus occupied positions in the food web that mirrored those of the vanished mosasaurs. This convergence extended to details of movement and hunting. Mosasaurs had deep, powerful tails and flippers that stabilized their bodies as they lunged forward. Later, tunas, lamnid sharks, and rorqual whales adopted comparable body outlines, using crescent or fluke-like tails to slice through the water with minimal drag. Different bones and tissues, different ancestries, but the same underlying engineering repeated across the planet's oceans. Then comes a quieter question. Do the oceans remember their former rulers? Individual empires fade from the sediment, but successful body plans and ecological roles return again and again. The shape of an apex hunter, the path of a fast pursuit through open water, the balance between predator and prey, these patterns persist even as new players rise to claim them. Predators vanish, but the patterns they once filled do not. When the last mosasaurs slipped into the sediment at the end of the Cretaceous, the role of swift reptilian hunter in the oceans did not disappear forever. It shifted into new bodies and new lineages that still move across Earth's surface today. The giant sea lizards belonged to a much broader reptile group known as the squamates, which also includes lizards and snakes. While the large marine branches of this group vanished during the end Cretaceous crisis, smaller, more generalist squamates survived. They occupied rivers, forests, coasts, and burrows, and during this time, their modest size and flexible diets helped them endure collapsing food webs. Over time, these survivors diversified again, radiating into many of the lizard and snake lineages that now occupy nearly every continent. Among them, monitor lizards stand out as particularly revealing relatives. These living reptiles share with mosasaurs a powerful elongated skull, recurved teeth, and a strong muscular body suited to both land and water. Some species, such as the Asian water monitor, prowl riverbanks and mangroves, diving with ease and pursuing prey in murky channels. This process of returning to semi-aquatic habits echoes the earlier transition that once carried mosasaur ancestors from shorelines into the open sea. Certain snakes also preserve elements of the mosasaur design. Flexible skulls with multiple joints allow them to widen their jaws and swallow prey larger than the head, a feature that parallels the double-hinged skulls of the giant sea lizards. Because of this shared architecture, both groups can exploit large, struggling prey, using recurved teeth to anchor and reposition their catch. In coastal regions, sea kraits and true sea snakes extend this strategy into marine environments, hunting fish and eels with paddle-shaped tails and lungs adapted for long dives. Another, more distant branch of the reptile family tree tells a different survival story. Birds, descended from small theropod dinosaurs, passed through the same extinction that ended the non-avian dinosaurs and many marine reptiles. Their light skeletons, insulating feathers, and varied beaks supported a remarkable radiation after the crisis. Today, seabirds such as albatrosses, penguins, and cormorants occupy aerial and coastal niches that mirror in a different medium the pursuit and ambush strategies once seen in marine reptiles. Modern marine reptiles also hint at ancient patterns. Sea turtles glide through warm oceans using powerful forelimbs and streamlined shells to cross entire basins. Sea snakes coil through coral reefs, while saltwater crocodiles patrol estuaries and coasts. As a result, reptilian life at sea did not end with the Cretaceous. It adapted, shifted, and found new forms. Yet these living echoes raise a larger question. If squamates, birds, and marine reptiles represent survivors of one great transition, how does their story fit into the deeper rhythm of Earth's changing continents, rising oceans, and repeating supercontinents? Their story fits into an even deeper pattern, one that stretches far beyond the age of dinosaurs or the reign of any single group of marine reptiles. Across Earth's long history, the rise and fall of ocean empires has followed the slow heartbeat of the supercontinent cycle. Pangaea was not the first time the continents gathered into one. Hundreds of millions of years earlier, an even older configuration called Rodinia had formed and later broken apart. Before that, other large landmasses such as Columbia assembled, collided, and fragmented. Geologists now expect that in the distant future, the drifting continents may again come together into a new supercontinent, sometimes called Amasia or Pangaea Proxima, closing the present oceans and creating new ones. Each cycle begins deep below the surface as heat in the mantle drives plates to move, converge, and separate. Continents collide and weld together, building high mountain chains and long enclosed coastlines. Over time, the joined mass begins to crack. Rifts open, volcanic ridges spread, and new ocean basins are formed, while older ones are slowly consumed at subduction zones. As a result, shallow continental seas appear and disappear. Gateways between oceans open and close, and global climate patterns are reorganized. During this time, marine habitats do not simply shift in place. They are repeatedly remade. Wide, warm epicontinental seas flood low-lying crust when continents sit near the equator. Narrow basins and steep continental slopes dominate when landmasses cluster toward the poles or when sea levels fall. Because of this, the opportunities available to marine reptiles, and even the kinds of prey that fill the water, change from one supercontinent cycle to the next. Early in the Mesozoic, after Pangaea first assembled, long coastlines and relatively simple ocean circulation favored early sauropterygians and the first ichthyosaurs. These reptiles evolved streamlined bodies, paddle-like limbs, and diverse feeding strategies that matched the broad, shallow shelves of Triassic and early Jurassic seas. Later, as Pangaea began to rift apart, new seaways and deeper basins formed. Plesiosaurs with long necks and short, powerful bodies spread through these reorganized oceans, while large pliosaurs hunted in cooler, nutrient-rich waters. By the late Cretaceous, the breakup of Pangaea had created complex arrangements of continents and mid-ocean ridges. High sea levels flooded the interiors of landmasses, forming inland seas, such as the Western Interior Seaway across North America. In this maze of shallow platforms and deeper channels, mosasaurs rose from small shore-hunting lizards to become apex predators, sharing the water with remaining plesiosaurs and giant sea turtles. No single lineage ruled all oceans for all time. Instead, each dynasty of marine reptiles flourished within a particular architecture of continents, ocean basins, and climate, then declined as that architecture shifted. This process links the drifting plates beneath the crust to the hunting grounds of giant sea lizards and the survival of their prey. If the continents gather again into a future supercontinent, what new seas will flood its lowlands, and what predators might evolve to patrol them? In a world with different coastlines, altered currents, and unfamiliar climates, the next rulers of the oceans may not resemble any reptile known from Earth's past. In the distant future, the drifting continents will not remain scattered forever. Geological models suggest that Earth is moving toward another phase in the supercontinent cycle. Over tens or hundreds of millions of years, the plates that carry the continents will continue to shift, collide, and reorganize until the land once again gathers into a single vast mass. Several possible arrangements have been proposed from this long-term motion of the crust. Some scientists envision Pangaea Proxima, where the Atlantic closes and the continents weld together roughly where the old supercontinent once stood. Others model Amasia, where the Americas and Eurasia converge around the North Pole. During this time, the exact layout will depend on how subduction zones migrate and how mantle heat drives convection beneath the plates. A new supercontinent would reshape the oceans as dramatically as the breakup of Pangaea shaped the Cretaceous seas. When land masses cluster, the surrounding ocean basins deepen in some regions and become shallower in others. This process alters global circulation, redirecting warm and cold currents and reorganizing storm tracks and rainfall. As a result, sea level relative to the continents may rise in some eras and fall in others, periodically flooding low-lying interiors. In such a world, broad inland seas could spread across continental lowlands, much like the western interior seaway that once split North America. Narrow marginal basins might open along rifted edges, forming long, semi-enclosed marine corridors rich in nutrients. Because of this, new ecological theaters would appear where coastal rivers, shallow shelves, and deeper basins meet, providing the same kinds of opportunities that once allowed mosasaurs to flourish. What kinds of predators might claim these future seas? The specific lineages are impossible to predict, but the selective pressures are familiar. Large-bodied hunters in open water tend to evolve streamlined forms to reduce drag, powerful tails or flukes for sustained swimming, and jaws specialized for gripping or slicing prey. Whether the next masters of the ocean are mammals descended from whales, teleost fish that expand into new roles, or entirely new reptilian branches returning from land to sea, convergent evolution will likely sculpt them into shapes that echo those of mosasaurs. Imagine a distant ocean where an air-breathing hunter with a deep, laterally flattened tail moves with the same sweeping strokes as a Cretaceous sea lizard, yet belongs to a very different branch of the tree of life. This pattern interrupt reveals an important point. The planet repeatedly runs similar experiments when similar environments arise. Tectonics sets the stage, climate and circulation tune the conditions, and ecological opportunity guides which designs thrive. Seen in this light, mosasaurs are not isolated curiosities from a lost age, but one successful solution in a long sequence of marine apex predators. Future supercontinents and future seas will host new actors, yet the underlying rules that shaped ancient reptilian hunters will continue to operate, preparing the way for the next generation of giants beneath the waves. Seen in this light, the question becomes clear. How can such vanished oceans and predators be known in detail at all? Millions of years ago, Earth had a very different arrangement of land and water. Yet the record of those seas still surrounds the planet in silent cliffs and plains of rock. Each layer holds traces of the Cretaceous world that formed above it. Sedimentary rocks are the primary archive of these lost environments. When fine muds, lime-rich shells, and coarser sands settled onto the seafloor, they built up in sheets that later hardened into shales, limestones, and chalks. Grain size, composition, and layering patterns record the energy and depth of the ancient water. Thick chalks, made from microscopic plankton shells, indicate warm, quiet, open oceans. In contrast, sandier beds with crossbedding and ripples point to shallower, wave-agitated shelves along shifting continents. Within these sediments, fossils preserve the inhabitants of those seas at multiple scales. Microscopic foraminifera and coccolithophores track changes in plankton communities and productivity. Ammonites, with their coiled shells, mark particular intervals of time and show how faunas spread between basins. Skeletons of fish, plesiosaurs and mosasaurs record the upper levels of the food web. As a result, entire ecosystems can be reconstructed, from the base of the food chain to the apex reptiles that patrolled the surface waters. Chemical signatures inside these rocks provide an additional line of evidence. Isotope ratios of oxygen in carbonate shells shift with water temperature and global ice volume. During this time, repeated measurements from different regions reveal that many Cretaceous seas were warm, even at high latitudes. Carbon isotopes show changes in the balance between buried organic matter and carbon released from the mantle, linking deep interior processes to surface climates. This process allows scientists to connect the life and death of marine reptiles to long-term cycles in Earth's carbon system. The rocks also record the motion of the crust itself. Tiny magnetic minerals align with Earth's magnetic field as sediments settle and as lavas cool. Over time, reversals of the magnetic field create a barcode-like pattern in the stratigraphic record. By matching these patterns globally and combining them with paleomagnetic directions, the past positions and rotations of continents can be traced. revealing how rifting and seaway formation open pathways for marine reptiles. One of the most informative archives from the Cretaceous is the Niobrara Formation of the Western Interior Seaway in what is now Kansas. Soft, chalky layers there were formed from the remains of plankton that blanketed a broad inland sea. Between these fine beds lie exquisitely preserved skeletons of mosasaurs, long-necked plesiosaurs, large sea turtles, and early birds with toothed jaws. Some fossils retain stomach contents and bite marks, recording predator-prey interactions with remarkable clarity. Because of this, the Niobrara acts almost as a series of still images from a vanished ocean. By reading these layered archives, a continuous narrative emerges, stretching from the molten early surface of the planet to the chalky seabeds where giant sea lizards once swam. The same mantle heat that drove plate motions also set the stage for these inland seas, and the next step is to follow that story forward to the final days of the Cretaceous oceans and the abrupt end of their reptilian rulers. The story of those chalky seabeds does not end in the Cretaceous. It continues in the cliffs, plains, and city foundations of the present. When the inland seas drained away and the last mosasaurs vanished, their oceans did not simply disappear. They were slowly buried, compressed, and transformed, turning soft muds and lime-rich oozes into the solid rocks that now shape many familiar landscapes. In many regions, the most striking example is chalk. The white cliffs of Dover, the broad chalk downs of southern England, and the chalky plains that underlie parts of Kansas and Nebraska, all formed from the same basic material. During this time, vast blooms of microscopic plankton rained down through the water column, their tiny calcium carbonate shells piling up on the seafloor. Over time, this process produced layers hundreds of meters thick. These layers hardened into chalk that now stands as steep coastal walls or lies hidden beneath fields and towns. These chalk and limestone bodies are not just scenic. They record entire food webs. The plankton that created them fed small fish and invertebrates, which in turn fed larger predators, including the giant sea lizards that cruised above. As a result, the very rock that now forms cliffs and plateaus is the frozen foundation of Cretaceous ecosystems. In the central part of North America, the former Western Interior Seaway left behind broad sheets of limestone and chalk, and within these rocks, skeletons of mosasaurs, plesiosaurs, and ancient sea turtles are found far from any modern coast. This inland setting often surprises those who encounter it. How can a farm in Kansas or a quarry in South Dakota hold the bones of marine reptiles? The answer lies in the shifting arrangement of continents and seas as Earth's crust responded to mantle heat and plate motions. Low-lying regions subsided, shallow waters advanced, and for millions of years, warm epicontinental seas covered the interior of the continent. When those seas finally retreated, they left their sediments behind as a silent record beneath the later landscape. These ancient marine deposits now play a direct role in human societies. Porous limestones and chalks often act as major aquifers, storing and transmitting groundwater that supplies cities and farms. Deeper in the sedimentary basins, organic rich layers derived from plankton and seafloor muds generated hydrocarbons as they were buried and heated. Because of this long burial history, many important oil and gas fields are hosted in Cretaceous marine sediments. Even building stones and crushed rock for roadbeds are frequently quarried from these former seafloors. Here, a pattern interrupt is useful. The next time a person steps across a polished limestone floor in a public building, or drives along a pale, chalk-rich road cutting through low hills, the support beneath is not just anonymous rock. It is the compacted remains of ancient seas, built grain by grain from the shells of plankton and the debris of long-vanished food webs. In many cases, those same layers once lay under the shadow of giant sea lizards, which hunted above them in green, sunlit water. Modern movement across these surfaces is, in a quiet way, a final passage over the worlds those reptiles once ruled. As the narrative turns toward the end of the Cretaceous, these everyday connections help frame what is at stake. The extinction of the marine reptiles did not erase their oceans. It transformed them into the very foundations of later environments, including the human world that now studies their remains. Those transformed foundations invite a direct comparison between the seas of the Mosasaurs and the oceans that surround the planet today. When the late Cretaceous reached its height, Earth was locked in a full greenhouse phase. Global temperatures were higher, polar regions held little or no permanent ice, and sea levels flooded the low-lying edges of continents, creating broad, shallow seaways that sliced into the interior of landmasses. During this time, atmospheric carbon dioxide was several times higher than modern pre-industrial values. The mantle released large volumes of volcanic gases along mid-ocean ridges and through massive igneous provinces, and this process kept the climate warm for millions of years. As a result, coastlines shifted far inland, and warm epicontinental seas became stable habitats. Today, the planet's climate is cooler in an absolute sense, but human-driven emissions are pushing CO2 levels upward at a pace that has few clear parallels in the geological record. The living communities within these oceans were also arranged very differently. In the late Cretaceous, large marine reptiles, such as Mosasaurs and the last Plesiosaurs, occupied the roles later filled by whales and giant sharks. There were no baleen whales filtering krill from the water, and several familiar shark lineages had not yet formed. Instead, ammonites spiraled through the water column in extraordinary diversity, taking ecological positions that now belong to squids, cuttlefish, and other modern cephalopods. Yet beneath these differences, the overall structure of the ecosystems followed patterns that are still recognizable. Apex predators hunted large prey and sometimes each other. Mid-level fishes, smaller reptiles, and invertebrates transferred energy from the surface waters downward. Plankton, floating near the sunlit surface, formed the base of the food web. Over time, evolution repeatedly produced streamlined, tail-powered swimmers, from ichthyosaurs to mosasaurs, and later to tunas, sharks, and dolphins, because of this consistent pressure to move efficiently through water. Modern coral reefs, upwelling zones, and broad continental shelves echo many aspects of those ancient seaways. Warm, clear waters over stable crust still favor reef-building organisms, even though corals and reef communities have changed since the Cretaceous. Regions where deep, nutrient-rich waters rise toward the surface still generate intense productivity, much as Cretaceous upwelling zones once supported dense populations of ammonites, fishes, and reptiles. Shallow seas that once covered the interiors of continents have withdrawn, but their former floors now hold thick, sedimentary layers packed with fossils. This parallel raises a pressing question. As human activity alters the atmosphere, warms the oceans, and raises sea level, are modern marine communities beginning to move toward conditions that once favored reptile-dominated seas? The rise and fall of the Mosasaur empires show that even the most successful ocean rulers depended on climate stability and reliable food webs. The next stage of the story asks what happened when that stability failed, and what that ancient crisis might suggest about the future of the oceans now forming around the changing Earth. When the stability of those Cretaceous seas finally failed, it did not fail slowly for the Mosasaurs. For more than 20 million years, they had ruled almost every warm ocean basin on the planet. Their fossils occur on former seafloors from Europe, Africa, the Americas, and the ancient margins of the great inland seaways. This wide distribution shows that they were not fragile curiosities, but a dominant and adaptable part of late Cretaceous marine ecosystems. Yet even this apparent security could not protect them from rapid, global-scale disturbance. When the asteroid struck at the end of the Cretaceous, it did more than remove sunlight. shock waves, wildfires, and the injection of dust and sulfur into the atmosphere changed the chemistry and temperature of the oceans. Plankton that formed the base of the food web declined. As a result, the rich chains of life that had supported giant sea lizards, large sharks, and long-necked plesiosaurs began to collapse from the bottom upward. During this time of crisis, large, specialized predators were among the first to disappear. Mosasaurs depended on dense populations of fish, ammonites, and other marine reptiles. When those prey groups faltered, the top predators had little buffer. This pattern appears again and again in Earth's history. Apex hunters vanish early in ecological breakdowns, not because they are weak, but because their success ties them tightly to the stability of everything below them. Their extinction becomes an indicator that the entire system has crossed a critical threshold. The end Cretaceous oceans also experienced acidification, cooling at the surface and expanding low oxygen zones as circulation patterns shifted. Modern oceans are now changing under a different kind of pressure. Instead of a single impact, human activity is adding heat, carbon dioxide, and nutrients to the seas over time. Ocean acidification, warming waters, and deoxygenation are altering habitats from coral reefs to polar shelves. Because of this, many scientists compare present trends to ancient crises, asking whether the planet is again moving toward conditions that undermine large marine predators. There is an important difference, however, between an asteroid strike and human-driven change. The impact was a sudden external shock, acting over years to centuries. Today's transformation is gradual on human timescales, but rapid in terms of geological history. This process gives societies some capacity to respond, yet it also risks pushing ocean systems past tipping points that are hard to reverse. Once food webs reorganize and extinctions cascade, recovery can take millions of years. Understanding how the Cretaceous seas failed offers more than a dramatic ending to the story of Mosasaurs. It provides a long view of what is at stake in the choices now shaping modern oceans. If past predators recorded the health of their ancient environments in their rise and fall, what might today's changing marine communities be recording in advance? The next part of the narrative turns from extinction to evidence, asking how rocks and fossils reveal these hidden warnings in Earth's deep history. To understand those warnings, the narrative has to widen again, stepping back from fossils on a single shoreline to the entire history of the planet that produced them. The rise of mosasaurs and other marine reptiles in the Cretaceous is only the latest chapter in a story that began when Earth itself first formed and began to cool. During its earliest history, the planet did not have blue oceans or stable continents. It was a molten world, its surface dominated by flowing rock and constant impacts. Intense heat from collisions, radioactivity, and pressure melted much of the outer layers. As a result, dense material sank inward to form the core, while lighter silicate material became the mantle and an early crust. When the surface finally cooled enough, water vapor condensed, rain fell for long intervals, and the first persistent oceans collected in low regions of the crust. Over time, this thin crust fractured into plates that began to move over the softer upper mantle. This process of plate tectonics built new seafloor at mid-ocean ridges, destroyed old crust in subduction zones, and slowly rearranged the continents. Earlier in Earth's history, these motions brought landmasses together into supercontinents such as Columbia and Rodinia, then pulled them apart again. Each cycle reshaped ocean basins, redirected currents, and altered climate patterns on a global scale. In the late Paleozoic, plate motions assembled a new giant landmass, Pangaea. This enormous continent stretched from pole to pole and was surrounded by a vast global ocean. Its interior held large deserts and extreme seasonal climates, while its long coasts framed marginal seas where early marine reptile lineages began to appear. When mantle heat eventually weakened parts of the crust, rifts opened, volcanism increased, and Pangaea started to break apart. Because of this breakup, new ocean basins formed and older ones narrowed or closed. By the Jurassic and Cretaceous, the continents had begun to separate into more familiar shapes, and rising sea levels flooded low-lying regions of the crust. Broad, shallow epicontinental seas spread across many areas. One of the most significant was the Western Interior Seaway, which split North America and connected the Arctic to the tropical Atlantic. During this time, similar basins formed around the world, creating extensive habitats where plesiosaurs, pliosaurs, sea turtles, and eventually mosasaurs could diversify and dominate. Seen in this longer perspective, the succession of marine reptile dynasties becomes part of a repeating pattern. Supercontinents gather, climates and coastlines change, extinction events prune ecosystems, and new groups rise in the altered oceans that follow. Mosasaurs, emerging from lizard ancestors about 100 million years ago, filled apex roles made possible by Cretaceous seaways sculpted by deep interior motions. The pattern interrupt is simple but profound. The history of a single group of predators cannot be separated from the slow choreography of plates, mantle, oceans, and climate that framed their entire existence. To follow that choreography back to its opening steps, the story must return to the first solid skin of the planet. Long before mosasaurs cruised Cretaceous seaways, the fate of their oceans was being written in the way Earth's crust first separated into lighter and heavier domains. When the early crust began to stabilize, small buoyant fragments formed that would later grow into continents, while denser basaltic plates built the floors of the first broad oceans. This initial differentiation was decisive. Without a contrast between light continental crust and heavy oceanic crust, there would be no long-lived continents to gather into supercontinents and later disperse. Over time, colliding fragments welded together into larger landmasses. These masses later assembled into Pangaea, then fractured into the scattered Cretaceous continents, whose margins framed the Western Interior Seaway and other marine basins. The presence of continents at all, and their capacity to move, came directly from that early separation of materials near the surface. Deep below, the mantle continued to convect, moving heat from the interior toward the crust. This process drove plates apart at mid-ocean ridges, where new seafloor formed, and pulled them down again at subduction zones, where old oceanic crust sank back into the mantle. Over billions of years, this slow cycling raised mountain belts, carved deep basins, and built broad continental shelves. As a result, the planet did not end up with a single uniform ocean, but with a complex pattern of shallow seas, narrow straits, and deep basins that changed through Earth's history. During this time, long-lived patterns in plate motions began to shape predictable environments. When continents stretched and thinned, low regions near their edges often sank below sea level, allowing marine waters to flood in. The Western Interior Seaway, which split North America during the late Cretaceous, was one such region. It occupied a broad sagging zone above a warm, subsiding lithosphere, fed by waters from widening ocean basins on either side. Similar processes created epicontinental seas on other continents, showing that these habitats were not accidents, but recurring outcomes of plate dynamics. Into these prepared arenas stepped the ancestors of mosasaurs. Shore-dwelling lizards, related to early monitor-like reptiles, hunted in warm coastal waters that existed only because rifting continents and high sea levels created extensive shallow shelves. As some lineages became more aquatic, developing stronger tails and flexible skulls, they exploited prey in these new interior seas. Because of this long geological backstory, the right coastlines, climates, and ecosystems were in place for mosasaurs to expand rapidly and become apex predators. Seen in this light, The evolution of giant sea lizards is one chapter in a narrative that stretches back to the planet's formation, to magma oceans, differentiating layers, and the first fragile crust. If the roots of mosasaurs reach that deep into Earth's interior and early history, what does that imply about the origins of later ocean rulers? Or even about the conditions that shaped the emergence of humans on land? And if the same forces are still moving the continents today, what further transformations might already be unfolding quietly beneath the surface? The same forces that opened Cretaceous seaways did not vanish when those oceans retreated. They continued to move the crust, to rearrange land and water, and to shape the stage on which later life, including humans, would appear. In a very direct sense, the continents that exist today are rearranged fragments of the same supercontinents that once bordered mosasaur-haunted seas. Over time, collisions and rifting recycled earlier continental pieces into new configurations. Ancient cratons that once sat near tropical shores of long-vanished oceans were carried thousands of kilometers, stitched into mountain belts, and stretched into passive margins. Because of this, the bedrock beneath many modern coastlines, plains, and cities includes rocks that formed beside Cretaceous seaways, or even beneath them when giant sea lizards hunted above. Human evolution unfolded on landmasses whose positions and climates were controlled by this same deep tectonic engine. When early hominins emerged in Africa, the continent already reflected a long history of rifting and uplift, driven by mantle heat and plate motion. Rift valleys, high plateaus, and shifting rainfall patterns influenced where grasslands expanded, where forests retreated, and where freshwater lakes formed. This process helped determine the habitats in which hominins learned to walk upright, to forage, and eventually to use tools. The arrangement of continents also guided ocean currents and monsoon systems, which in turn shaped the climates that later framed the rise of agriculture in cities. When ice sheets advanced and retreated, sea level changed, exposing land bridges or flooding low coasts. These shifting shorelines echoed far older changes that had once created inland seas for mosasaurs. During this time, the same planetary mechanisms that built marine reptile habitats were quietly preparing the environmental backdrop for human societies. Modern economies depend heavily on materials that were deposited in ancient environments, including those Cretaceous seas. Thick sequences of carbonate rocks, formed from the shells and skeletons of marine organisms, now host aquifers, building stone, and important ore deposits. Organic-rich muds that settled in quiet seafloor basins became, under pressure and heat, the petroleum and natural gas that power transportation and industry. As a result, fuels burned in modern engines often come from sediments laid down while mosasaurs cruised above. In this way, human civilization is tied to the same long narrative as the giant sea lizards. Both represent temporary peaks of ecological dominance, separated by tens of millions of years, but governed by the same physical constraints of plate tectonics, climate feedbacks, and resource limits. What happens when those limits are pushed too far? Here, a pattern emerges that interrupts the sense of human uniqueness. Studying Cretaceous sea lizards does more than reveal a lost ocean ecosystem. It exposes the preconditions for human existence itself. The same shifting continents, evolving seas, and buried sediments that sustained mosasaurs also set the stage for primates, for cultures, and for the modern world that now looks back at them. So it is time to sink again beneath a Cretaceous sea. But now the scene carries labels and histories, rather than only shadows and motion. Millions of years ago, Earth had a very different arrangement of land and oceans. The continents were no longer joined as Pangea, but spread apart into broad fragments that framed warm inland seas. Into one of these basins, the viewer descends once more. Near the sunlit surface, the water looks almost empty from a distance, yet it is thick with life. Tiny plankton drift in enormous numbers, their delicate shells forming a slow rain of calcium carbonate. During this time, each microscopic plate that settles toward the seafloor adds to a future layer of chalk. Over time, this process will build the pale cliffs and plains that later humans will stand upon, without realizing that the rock beneath their feet once floated in this shimmering light. Just below, larger shapes begin to resolve. A long-bodied mosasaur, perhaps 15 meters in length, moves with the slow confidence of an apex hunter. Its tail, deepened into a powerful fin, beats in steady strokes. Double-hinged jaws and recurved teeth show an animal adapted to seize and swallow large prey. Around it, other mosasaurs patrol different depths, some built for speed near the surface, others heavier and suited to diving after deep-swimming fish and squid. Sharing this realm are plesiosaurs and their broad-headed relatives, the pliosaurs. Long-necked forms glide with 4 wing-like flippers, ideal for sudden turns as they ambush schools of fish or small ammonites. Shorter-necked, massive-skulled pliosaurs are shaped for burst attacks on larger prey. Nearby, large sea turtles with strong paddle-shaped limbs move more slowly, protected by shells that turn many attacks into glancing blows. Each group holds a different role, dividing the resources of the basin. Closer to the seafloor, clouds of fish and coiled ammonites feed on the drifting organic rain from above. Ammonites use coiled shells for buoyancy and maneuvering, their tentacles searching the water for particles and smaller animals. When a mosasaur or pliosaur passes, sudden shifts in direction reveal a constant tension between predator and prey. Because of this continuous pressure, streamlined bodies, sharp senses, and rapid growth are favored over generations. Around the basin, the continents are not fixed boundaries but moving walls. North America, Africa, and other landmasses slide across the planet's surface, carried by plates riding the mantle's slow convection. This motion opens seaways, narrows straits, and redirects currents. As a result, water temperature, salinity, and nutrient flow change, which in turn shapes where plankton thrive, where reefs can form, and where giant reptiles can find enough food to reach such sizes. Every element in this ocean is a product of deep time. The predators owe their existence to earlier lizards that once walked on land. The prey depend on chemical conditions set by volcanic gases, by weathering crust, and by circulation patterns rooted in plate tectonics. Even the basin itself formed through stretching and bending of the lithosphere, guided by mantle heat and the long supercontinent cycle. Holding this layered picture in mind turns a single ancient sea into a record of the entire planet. It invites a different view of the present world as well. If drifting plates, changing chemistry, and evolving lineages once produced this Cretaceous ocean, what kind of future oceans are now being formed beneath the surface of the modern Earth? Seen in this light, mosasaurs become more than dramatic predators. They become a clear demonstration of how quickly life can respond when new environments open. In a span of only a few million years, modest shore-dwelling lizards, related to early monitor lizards and snakes, shifted their limbs into flippers, lengthened their bodies, and developed powerful, tail-driven swimming. During this time, some lineages expanded from small coastal hunters to giants more than 15 meters long that ruled the open ocean. This rapid rise illustrates evolutionary innovation operating under strong ecological opportunity. As older marine reptiles declined or disappeared from certain regions, vacant roles in the food web appeared. Mosasaurs evolved flexible skulls, double-hinged jaws, and rows of replacement teeth that allowed them to grasp, reposition, and swallow large prey. Over time, these anatomical changes, combined with improved swimming and keen senses, turned a shoreline experiment into a successful global radiation. However, their story only makes sense when placed in the wider context of the Cretaceous Earth. The breakup of Pangaea had already rearranged the continents, opening broad new ocean basins and long, shallow seaways such as the Western Interior Seaway across North America. tectonic plates moved apart, mid-ocean ridges released heat and new crust, and high sea levels flooded continental margins. Because of this, warm, well-lit epicontinental seas formed ideal habitats for marine reptiles to diversify and spread. At the same time, the Mesozoic marine revolution reshaped ocean ecosystems. New types of shell-crushing predators, burrowing animals, and fast-swimming fish altered how energy and nutrients moved through the water. This process favored agile, visually oriented hunters that could track and overpower active prey. Mosasaurs, plesiosaurs, and large sea turtles each occupied different roles within this evolving seascape, showing how geology, climate, and biology interacted to build entire communities. Yet even the most successful forms remained vulnerable to sudden planetary change. When an asteroid impact and intense volcanism disrupted climate and ocean chemistry at the end of the Cretaceous, the giant sea lizards vanished along with many other dominant groups. Apex predators, broad seaways, and long-established food webs collapsed in a relatively brief interval. As a result, the ocean biosphere reorganized, and later lineages such as whales and modern sharks rose into niches once held by mosasaurs. The geological record preserves this transformation not as isolated bones, but as a connected narrative. Rock layers capture changing sea levels, shifting temperatures, and the chemistry of ancient waters. Fossil communities show which organisms flourished or failed as conditions changed. Together, these lines of evidence reveal a planet whose crust, mantle, oceans, and atmosphere have always been linked to the history of life. If a single chapter about giant sea lizards can expose such deep connections between Earth's interior, its surface seas, and its living inhabitants, what might other intervals of time reveal? What stories lie hidden in older supercontinents, earlier crises, and different oceans? And as the timeline of Earth's history broadens again, which chapter should be open next? To explore those next chapters, it helps to return to a very familiar scene. Imagine standing on a present-day shoreline, perhaps beside a harbor, a sandy beach, or a rocky cliff where waves strike the land. The air carries salt and wind, modern ships cross the horizon, and the boundary between land and ocean seems clear and permanent. Now the timeline shifts. During this time, the same location may have looked entirely different. Instead of a single coastline, an inland sea could have extended far into what is now the interior of a continent. A city that exists today might lie beneath hundreds of meters of warm Cretaceous water, its place on the map occupied by a broad, shallow seaway where giant sea lizards hunted above drowned plains and buried river valleys. Beneath that modern shoreline, the ground is not a simple, solid platform. It is a layered archive. Near the surface, recent beach sands and dune deposits record storms, tides, and changing sea levels. Below those lie older river gravels, floodplain muds, and soils from earlier landscapes. Deeper still, there may be marine sediments left by vanished oceans, fine muds that settled in quiet water, shells of plankton that rained down through the water column, and carbonate layers that formed as organisms built skeletons and dissolved again over time. This vertical stack of materials shows how the planet's surface has changed. As continents shifted and sea levels rose and fell, shorelines advanced and retreated. Each advance laid down new marine layers. Each retreat exposed land to rivers, plants, and erosion. Over time, this process recorded the movement of plates, the influence of mantle heat on ocean basins, and the changing climates that shaped where reptiles, fishes, and other organisms could live. These changes are not only preserved in distant exotic locations. Many regions contain nearby evidence of ancient seas and marine reptiles. A local museum may display mosasaur jaws from an inland seaway, plesiosaur vertebrae from chalk cliffs, or ammonites collected from road cuts. A short visit to a fossil site, a quarry wall, or an eroded riverbank can reveal shells in limestone, ripple marks in sandstone, or dark shales that once accumulated in oxygen-poor sea floors. Because of this, the history of giant sea lizards becomes connected to everyday surroundings. Understanding deep time is not an abstract exercise. It reshapes how coastlines, weather, and even built environments are viewed. The stone in buildings, the gravel beneath roads, and the metals in infrastructure all come from rocks that formed under ancient oceans, mountain belts, or volcanic arcs. As a result, modern landscapes and materials become links to earlier chapters of Earth's history, rather than separate from them. Here, a pattern can shift again. The next time a map, a cliff face, or the surface of the sea is observed, a dual vision can be carried: the present-day world and the deep-time world beneath and before it. What other hidden shorelines and lost habitats might be waiting behind that second view? Seen through that second view, the story of the giant sea lizards stretches back far beyond their teeth and bones. Long before any mosasaur swam, the planet formed from dust and rock around the young sun, its surface shaped by intense heat and continual impacts. As the mantle convected and the first crust hardened, plate tectonics began, setting continents on slow paths that would, over time, rearrange entire oceans. During this time, supercontinents assembled and broke apart. Pangea was only one chapter in that longer cycle, but its breakup was crucial for the later marine reptiles. As rifts opened and new oceanic crust formed, the Atlantic widened and shallow seaways invaded low-lying interiors of continents. Because of this, the Cretaceous world contained broad, warm epicontinental seas, flooded by high global sea levels and heated by an atmosphere rich in greenhouse gases. Within these new habitats, marine reptiles followed earlier pioneers into the water. Ichthyosaurs, which had already dominated earlier Mesozoic oceans, gave way to other groups as climates and coastlines shifted. Plesiosaurs, with long necks or massive skulls, cruised the shelves, while early sea turtles experimented with life far from shore. This process of repeated invasion and adaptation created a layered marine fauna by the mid-Cretaceous. From this background, mosasaurs emerged. Descended from shore-hunting lizards related to modern monitors and snakes, they first occupied nearshore environments, their limbs and spines only partly modified. Over time, their bodies transformed. Hind limbs and forelimbs became powerful flippers. Vertebrae supported a deep, tail-driven fin, and skulls developed flexible joints and double-hinged jaws. As a result, some species exceeded 15 meters in length and took over the apex roles later filled by giant sharks and whales. The Western Interior Seaway, which split North America, became one of their primary arenas. Its warm, moderately deep waters held long-necked plesiosaurs, massive sea turtles, sharks, and large bony fish. Mosasaurs hunted among them, using sensitive snouts, shark-like tooth replacement, and strong tails to ambush prey. Fossils with stomach contents and bite marks show them consuming fish, ammonites, turtles, and even other mosasaurs. In such a world, what did it mean to be safe? This marine tapestry did not last. Around 66 million years ago, the Chicxulub impact struck the planet, triggering shockwaves, wildfires, and a global dust veil. Photosynthetic plankton declined, food webs faltered, and the great reptiles of the seas vanished alongside non-avian dinosaurs on land. Ichthyosaurs were already gone. Now mosasaurs and most plesiosaurs disappeared as well. Sharks, ray-finned fish, and later, marine mammals such as whales expanded into the vacant roles. The present oceans still carry this history. Modern continents reflect the long breakup of Pangea. Present currents and climates follow patterns first imposed by shifting plates and changing seaways. When a shoreline is traced on today's maps, it outlines basins once filled by ammonites and giant lizards. What other connections between ancient seas and the modern world remain to be uncovered next? The present oceans still carry this history, but they also carry a warning. When the age of the giant sea lizards is viewed against the full span of Earth's history, it becomes clear that oceans, climates, and living communities are not fixed. They are outcomes of long interactions between the crust, the mantle, the atmosphere, and life itself. What changes when those interactions are suddenly pushed in a new direction? During this time in the late Cretaceous, tectonic forces that began with the breakup of Pangaea had opened broad seaways and rearranged continents. Warm conditions, high sea levels, and rich, shallow basins allowed mosasaurs to expand from small shoreline hunters into dominant ocean predators. Over time, entire food webs organized themselves around these reptiles, from microscopic plankton at the base to the largest lizards at the top. This process created systems that looked stable and enduring on human timescales. Yet the end of the Cretaceous shows how quickly such apparent stability can fail. When the asteroid struck and volcanic activity altered atmosphere and ocean chemistry, the foundation of those marine ecosystems began to collapse. Plankton communities changed, photosynthesis faltered, and the fine balance of temperature and acidity shifted. As a result, apex predators like mosasaurs, plesiosaurs, and large marine reptiles disappeared in a geologic instant. Their size and dominance did not protect them when the base of the system was removed. This vulnerability is central to the present day. Plate motions and asteroid impacts lie far beyond human influence, but greenhouse gas levels and ocean chemistry do not. The same planet whose mantle heat drives plate tectonics now carries an atmosphere rapidly altered by industrial activity. Because of this, the oceans are warming, expanding, and becoming more acidic at rates that rival some of the faster changes in the rock record. Coral reefs, plankton, and coastal ecosystems that support modern fish, sharks, and whales are beginning to experience stresses that, in deep time, often preceded major ecological shifts. The story of the giant sea lizards therefore acts as more than a distant curiosity. It demonstrates that apex predators, whether mosasaurs in inland seaways or large sharks and marine mammals in modern oceans, depend on conditions that can unravel if the underlying climate and chemistry move beyond certain limits. It also shows that recovery, when it occurs, unfolds over millions of years, not centuries. Deep time narratives like this one can cultivate a different attitude toward the present oceans. They invite humility in the face of a planet that has erased entire dynasties, curiosity about how Earth's interior and surface are linked, and a sense of stewardship toward the marine systems that now support human societies. If this journey through ancient seas has shifted how the water at a shoreline or the ground beneath a city is perceived, the next step is to look for concrete ways to keep exploring, sharing, and applying that broader perspective. If the ground beneath a city or the waves along a shoreline now feel connected to ancient seas, that new perspective can be extended further. The Cretaceous oceans, the breakup of Pangaea, and the rise of giant sea lizards form only one chapter in a much longer record that can be explored in many ways. The next steps involve turning a single story into an ongoing relationship with Earth's deep history. One path leads through books and documentaries that focus on these ancient oceans in more detail. Accessible overviews of marine reptiles introduce mosasaurs, plesiosaurs, and Cretaceous sea turtles, explaining how their skeletons and teeth record their hunting strategies. Works on plate tectonics show how the same moving crust that once brought continents together into Pangaea later tore them apart, opening the Atlantic and creating inland seas such as the Western Interior Seaway. Documentaries that follow research teams into quarries, sea cliffs, and drilling ships reveal how this process of reconstructing vanished ecosystems actually unfolds. Another path lies in physical spaces where deep time is preserved. Natural history museums often devote entire halls to marine reptiles from the Cretaceous, displaying articulated mosasaur skeletons with preserved stomach contents or plesiosaurs whose long necks still curve through the rock. Wall maps trace the changing positions of continents, showing how the oceans that formed during this time covered regions that are now dry land. Standing beneath these reconstructed animals, provides a direct sense of scale that illustrations on a page cannot fully convey. Exploration can also begin close to home. Geological maps, often available online, show which layers of rock lie beneath towns, fields, and coasts. By comparing these maps with timescales, it becomes possible to see whether local formations were deposited in shallow seas, river plains, or deep ocean basins. In some regions, marked fossil sites and safe, supervised outcrops allow visitors to walk across former seafloors and, in rare cases, observe fragments of ancient shells or vertebrate bones in the rock. Because of this, a familiar landscape can start to feel like a record of vanished shorelines. Digital resources extend this search even further. Online databases curated by museums and geological surveys list mosasaur and other marine reptile fossils by age and location, often including photographs, maps, and scans of the original specimens. Interactive plate reconstruction tools allow the continents to be moved backward in time, reconnecting them into Pangaea or spreading them apart into the Cretaceous configuration that supported vast inland seas. Over time, these tools make it easier to visualize how changes in the mantle and crust reshaped habitats and guided evolution. Connections with institutions can turn curiosity into participation. Local natural history museums and university outreach programs frequently host lectures on paleontology, run fossil identification days, or invite visitors behind the scenes to observe collections. Citizen science initiatives sometimes ask volunteers to help classify fossil images, report new finds, or assist with geological mapping. As a result, the boundary between observer and contributor becomes less rigid, and personal observations can feed into broader scientific projects. Sharing this new understanding is another important step. Conversations with friends, classroom presentations, digital art of mosasaurs hunting in inland seas, or thoughtful posts on social media all help spread a deep-time perspective. When more people recognize that the present oceans sit atop a layered history of earlier seas, predators and climates, everyday decisions about coasts, resources, and conservation can be informed by that longer view. This channel is intended to function as a continuing guide through Earth's hidden timelines and lost ecosystems. Each episode follows the same planet through different configurations of continents, climates, and life, tracing how interior heat and plate motion shaped opportunities and extinctions. The next call to action will invite a deliberate step deeper into that journey, turning passing interest in giant sea lizards into a sustained exploration of the planet's changing oceans. In this episode, the story began in the shadow of a single giant predator, a mosasaur rising from a warm inland sea. Over time, that single encounter expanded into a wider view, linking one animal's jaws and tail to the drifting of continents, the opening of oceans, and the final collapse of an entire marine world at the end of the Cretaceous. The emotional path moved from immediate awe to deeper connection. At first, the focus rested on teeth, flippers, and the silent power of a tail-driven body cutting through the water. During this time, the mosasaur appeared as an isolated marvel. As the narrative unfolded, that same body became evidence of larger forces: Pangaea's breakup, rising sea levels, and the creation of vast seaways that flooded the interior of continents and formed new habitats above the shifting crust. Along the way, the episode followed the rise of these giant sea lizards from small shoreline hunters to apex predators that shared their oceans with plesiosaurs, sea turtles, and the last ichthyosaurs. This process connected individual fossils to entire ecosystems, showing how plate motion, mantle heat, and changing climates opened and closed pathways for life. As a result, the fall of the mosasaurs at the end Cretaceous impact did not stand alone, but became one chapter in a longer history of extinctions and survivals on this planet. Standing at this point in Earth's history invites a final question. How many other chapters remain hidden in older rocks and deeper layers? Earlier supercontinents, such as Rodinia or Columbia, held their own inland seas, reefs, and predators that have not yet been fully explored on screen. Future episodes will move across different arrangements of continents and oceans, tracing how new coastlines, changing atmospheres, and rising or sinking seafloors shaped unfamiliar ecosystems and vanished creatures. For viewers who wish to continue this slow journey through deep time, a simple step helps keep the story connected. Subscribing, liking, and sharing signals that there is interest in more soft-spoken explorations that link large-scale planetary changes to the daily lives of ancient organisms. Because of this, each new release can build on the last, following the same planet as its crust shifts, its oceans reorganize, and its living communities adapt or disappear. Comments can also guide where the narrative turns next. Which part of the Mosasaur story felt most surprising? Their rapid evolution from small lizards, their dominance of inland seas, or their sudden disappearance after the impact? Which ancient oceans should be visited in future episodes? The early Paleozoic seas of trilobites, the Jurassic basins of long-necked plesiosaurs, or the first whale-dominated coasts? As the episode closes, the image returns to the modern ocean at dusk. The surface lies calm, broken only by gentle ripples that catch the last light. Far below, layered rocks record older shorelines, once lying beneath the flukes and tails of giant sea lizards. The sea grows dark for now, but the story of this planet continues, waiting in the next chapter for those who choose to remain and listen.